Let's practice reviewing a bunch of Algebra 1 together. Now real quick before we get started, if you'd like to download a free copy of this blank PDF, you can find a link to that in the description box below. Using that link below, not only will you find an annotated answer key for this PDF, but you'll also find a bunch of other resources that I've made as well that'll hopefully be helpful. While Algebra 1 covers a bunch of different concepts, I've condensed them the best I could into 60 different practice problems. So let's go ahead and get started. I encourage you to grab some paper, something to write with, and let's do some math together. All right, so for number 1, we have this equation. Let's go ahead and start by distributing this -2, just because it means multiplication. That's got to go first here. So if we do that, we're going to have 7y. And then if we take away 6y, because -2 times 3 is -6, then -2 times -1 is going to be +2. That's going to be equal to 4. All right, next we're going to go ahead and combine some like terms. So this 7y minus the 6y here, that's going to be a total of 1y, or just y. So we're going to have y plus 2 is equal to 4. At this point, we just have a one-step equation, so we can go ahead and use the subtraction property of equality and take away 2 from both sides. If we do that, those 2's are going to cancel out to make 0, and we can say that y is equal to 2. So that would be our answer for number 1. Here's number 2. For number 2, it says the sum of 3 consecutive odd numbers is 117. What are the 3 numbers? I'm going to go ahead and use equations to go ahead and solve this. So for the 3 consecutive odd numbers, to write an expression that represents an odd number, you can use something like this, where you have 2n plus 1. You could also use 2n minus 1 if you want, but if you double any number and add 1, you will always get an odd number. So this will be the first number, and then the second number, I'm going to call that one 2n plus 3. Because remember, odd numbers are always 2 away from each other. And then I'm going to call the third odd number 2n plus 5. All right, so this could represent our first number. This one over here would represent our second odd number, and this would represent our third odd number here. So now let's go ahead and write an equation here. They say the sum of these 3 integers adds up to 117. So the first one is 2n plus 1. The second one is 2n plus 3. And the third one is this 2n plus 5. They say the sum is equal to 117, so let's set that equal to 117. Okay, at this point, let's go ahead and simplify this equation. All the parentheses don't matter, they were just there to kind of help us group a little bit. 2n plus 2n plus 2n, that's going to combine to make a total of 6n. And then if we go ahead and combine these other constant terms here, 1 plus 3 plus 5. 1 plus 3 plus 5, that's going to be 9, so we have 6n plus 9, that's equal to 117. All right, so this looks like a two-step equation. Let's go ahead and subtract 9 from both sides using the subtraction property of equality. That 9 and -9 are going to cancel out to make 0. So we're going to have 6n is equal to 108. And then finally, we can use the division property of equality and divide both sides by 6 here. If we go ahead and do that, we're going to get 1n, or just n, and that's going to be equal to, let's see, 18. Okay, so all right, so now that we know that n is 18, let's go ahead and substitute it in here. If we do 2 times 18, that is going to be 36 plus the 1, so that's going to be 37. So this first number here is going to be 37 for our first odd number. Then let's go ahead and take that 18 here, plug it into our second expression. So 2 times 18 is 36, plus the 3 is going to be 39. So that second integer is going to be 39. And yes, these are consecutive odd numbers. And then finally, we'll take this 18, plug it in over here. 2 times 18 is 36, plus 5 is 41. So this third number is going to be 41. So the question asks us here, what are the 3 numbers? The 3 numbers are going to be 37, 39, and 41. Here's number 3. For number 3, let's go ahead and solve this equation here. So it looks like we have an equation that has some fractions as well. Let's see here. If we don't want to deal with fractions at all, we could multiply this entire equation by the LCD, or least common denominator. So I'm actually going to do that first here. I'm going to take this entire equation, the left side and the right side, and it looks like the two denominators here are 4 and 2. So the least common denominator would be 4. So if we multiply the entire equation by 4, 4 would multiply by just this 3/4 here, and the 4's would cross cancel here. We just have 3. So on the left side of the equation, we would have 3, and then we have this 8x minus 6. Okay, and then if we go ahead and take this 4 and distribute it to this -2, 4 times that -2 would be -8. Then if we take this 4, distribute it to this half, 4 times a half, that's going to be 2. And then minus, and take this 4 and distribute it to this -x. 4 times that -1 in front for the x, for the coefficient, is going to be -4x. Okay, so we just went ahead and distributed to each of the terms there, and then we have an equation that has no fractions, which is kind of nice. Let's go ahead and now actually distribute this 3, which is nicer than distributing the fraction. 3 times 8x, that's going to be 24x. 3 times this minus 6 is going to be minus 18. We have a minus 8, and that's equal to 2 minus 4x. All right, so let's go ahead and combine some like terms on the left side. So we have this negative 18 and negative 8. If we combine those, we're going to get 24x minus 26 is equal to 2 minus the 4x. Alrighty, so let's go ahead and try to get our like terms on the same side here. So I'm going to get the x's to the left side by using the addition property of equality. I'm going to go ahead and add 4x to both sides here. If we do that, then on the left side, 24x plus 4x, that's 28x minus 26 is equal to 2. Then we can use the addition property of equality and combine the constant terms on the right side. Go ahead and add 26 to both sides. If we do that, we're going to get 28x is equal to 28. And finally, we can use the division property of equality and divide both sides by 28. If we go ahead and do that, then we're going to get x is equal to 1. So that would be our solution. For number 4, we have this equation relating Fahrenheit and Celsius, and it says that we need to go ahead and solve this for Celsius. So right now we have the equation Fahrenheit is equal to 9/5 multiplied by whatever the Celsius temperature is, plus 32. And it says solve it for C, so we need to get C alone, okay? First thing we're gonna do here is let's go ahead and subtract 32 from both sides. Okay, using that subtraction property of equality. If we do that on the left side, we're going to have f minus 32. We can't combine those. That's going to be equal to 9/5 multiplied by c. Okay, now how are we going to get c to be alone or to have a coefficient of 1? Well, we can actually take both sides of this equation and we can multiply it by the reciprocal of 9/5, which is going to be 5/9. All right, now why are we going to do that? Well, if we go ahead and multiply this 9/5 over here by 5/9 on the right side, these 9s will cross cancel and the 5s will cross cancel, and we just left with 1c, or just c on the right side, because everything's going to cancel out. And on the left side, we're going to have to take this 5/9 and distribute it to the f, then distribute it to the negative 32. Okay, so depends how you want to write that, but I'm going to go ahead and just write it like this first. So 5/9 multiplied by that Fahrenheit temperature minus 32. Okay, so you can write it just like this. But if you also want to distribute it, you can, and say that the Celsius would be equal to 5/9 of whatever the Fahrenheit temperature is, minus, and then we can multiply that 5/9 here by this negative 32, but unfortunately we can't cross cancel. So I believe that would be minus 160 over 9. So it depends how you want to write it. Either of these last two steps are pretty good, but you can go ahead and isolate that Celsius temperature just like that. All right, here is number 5. For number 5, we're going to go ahead and try solving this inequality. Looks like we have a bunch of properties we got to use here. So let's start with using the distributive property on the left side. Let's distribute this 5 to both of these terms here. So 5 times x, that's 5x. Then 5 times 1 is just going to be 5. Then we have minus 10. It's going to be greater than or equal to, and then we have 2x plus. Then we're going to go ahead and distribute this 3 to the x and 3 to this 2. So 3 times x is going to be 3x, then 3 times 2 is going to be 6. All right, on the left side of this inequality, it looks like we have some like terms. Let's go ahead and combine this positive 5 and negative 10. So let's go ahead and say that's going to be 5x, and then 5 minus 10, that's going to be negative 5. That's greater than or equal to. And on the right side, we can combine this 2x and 3x. That's going to make 5x. So we have 5x plus 6. All right, next we're going to go ahead and use some properties of equality. Let's start by subtracting 5x and 5x. Something interesting is going to happen here, it looks like. If we go ahead and do that, then the 5x's will cancel out on the left side. So we have negative 5 is greater than or equal to, but then on the right side, this 5x's cancel out as well, and we have negative 5 is greater than or equal to 6, which is not true, right? So for this particular equation, or inequality rather, we can say that there's no solution. So there's no value for x that would ever make this true, and that's that fancy symbol for no solution. All right, here is number 6. In this one, we are going to go ahead and solve and graph the solutions for the following inequality. Looks like we can jump right into using some POEs to move things around. So just copying the problem down, we have 3x plus 8. That's greater than or equal to 5x minus 14. I like getting my variables to the left side, so I'm going to go ahead and minus 5x and minus 5x from both sides here. If we do that, then 3x minus 5x is going to be negative 2x. And we have plus 8. That's going to be greater than or equal to negative 14. And then we can go ahead and take away 8 and take away 8 from both sides. If we do that, then we're going to get negative 2x is greater than or equal to negative 22. And here you got to remember that if you divide both sides by negative 2 here, that we have to flip the inequality. So we're actually going to get x is less than or equal to positive 11. Okay, so that would be the solution for this inequality. Now in terms of graphing the solution, nothing too fancy here, but let's just go ahead and make a quick number line. Let's put 11 in the middle. I'll put one number to the right. I'll say that's 12 and then 10. And then we're going to put a closed circle on 11. So remember, if it's equal to 11, you're going to fill it in, but if it's not equal to or can be equal to, then you would leave a hollow circle or an open circle. So draw an arrow to the left here, but this would be a graph for the solutions. All right, over for number 7, looks like we have a compound inequality. So it looks like we have a couple parameters on the left side and the right side. So if we go ahead and solve this, let's go ahead and just copy it down first. We have negative 36 is less than or equal to this 2x plus 4, which is smaller than 48. For compound inequalities, right, if you go ahead and take away 4 in the middle, just make sure you take away 4 from all the different parts of it. So there's 3 kind of sections here. Negative 36 minus 4 is negative 40. Is less than or equal to, and then the 4s are going to cancel out. So you just have 2x, which is less than 44. Okay. And then if you want to go ahead and get x to have a coefficient of 1, you can divide all 3 sections by 2. So we're going to get negative 20 is less than or equal to 1x, or just x, which is less than 22. All right, so what we just found here is that x would have to be between negative 20 and positive 22 to be a solution here. So that would be our final answer. And in terms of a graph, we can go ahead and just make a quick number line. Negative 20 would be somewhere down here to the left. 0 would be maybe somewhere over here. 22 would be a little bit farther to the right. And it looks like we're going to have a closed circle on negative 20. So let's go ahead and put a closed circle right over here. And it looks like we're going to have an open circle on the 22. So x is not allowed to equal 22, but it can equal negative 20, and then anything in between is fine. So there would be a graph for the solutions. Here is number 8. For number 8, we have some more inequalities here. This is another compound inequality. Let's deal with one part at a time. This is an OR, so we know the arrows are going to go in different directions. So we have 9 minus 4x is greater than 5. I like my variables on the left, so let's go ahead and take away 9 and get the constants together on the right side. So 9 minus 9, that's going to be 0. We're going to get negative 4x is going to be greater than negative 4. And then we can divide both sides by negative 4. But be careful, when we do that, we have to flip the inequality symbol. So we're going to get x is going to be less than positive 1. Now the other part to this problem is we have this 4 being multiplied by this negative 1 plus x minus 6, which is greater than or equal to 2. This one's a little bit more complicated, so we got to start by distributing this 4 to both of these terms. That's going to be negative 4 plus 4x minus 6 is greater than or equal to 2. Then on the left side, I think we can combine some like terms. We have this negative 4 and negative 6. So if we combine those, we'll get 4x minus 10 is greater than or equal to 2. Now it's just a two-step inequality. Let's add 10 and add 10 to both sides. Then we're going to go ahead and say that this 10s are going to cancel out. So we have 4x is going to be greater than or equal to 12. And then finally, we can divide both sides by 4 here. And don't flip the inequality because we're just dividing by a positive. So x is going to be greater than or equal to 3. So putting these two solution parts together, we can say that x could be less than 1, or we can say that x could be greater than or equal to 3 in order to make this inequality true. All right, so the compound inequality. Graphing this, what would it look like? Well, we can make a number line here, and let's go ahead and put 0 somewhere over here. Maybe 1 would be here. I can put 2 in between 1 and 3, just like that. X has to be less than 1. That's one possibility. I'm going to draw that going to the left, or it could be greater than or equal to 3. So fill that circle in on 3 and then draw an arrow to the right. All right, for number 9, we have an absolute value inequality. So keep in mind that these are going to have either 0, 1, or 2 solutions. In this case, I think we're going to have 2 because you can take the absolute value of something and get 10. So when you have absolute value equations, you're going to want to split this into 2 different equations. So the first one would just be 3 minus x, and that's going to be equal to 10. And the second one is going to be 3 minus x, and that's going to be equal to the opposite of 10, or negative 10. Okay, so when you're doing these absolute value equations, make sure the bars are alone first, and then go ahead and split into 2 different versions. On the left side, let's go ahead and take away 3, take away 3. If we do that, we're going to be left with negative x is equal to 7. And to get rid of that negative in front of x, which is a negative 1, being multiplied by it, we can divide both sides by negative 1 and say that x could equal negative 7 here. Now, in our other scenario, let's go ahead and take away 3 as well. If we do that, those 3's will cancel out. We'll have negative x equals negative 13. And then we can divide both sides or multiply both sides by negative 1. And if we do that, we're going to find out that x is equal to positive 13. Okay, so our solutions here, we can say that x can equal negative 7, but x can also equal 13. Those would be the 2 solutions that would make this true. For number 10, we have an absolute value inequality. So before we can split this into 2 different little inequalities, what we need to do is isolate the absolute value bars. So in the last problem, it was already by itself, but this one has this minus 1 that's kind of hanging out on the same side. Let's go ahead and add 1 to both sides first. That way we can get the absolute value bars isolated. So we're going to have the absolute value of 2x minus 3, and that's going to be greater than 5. Okay, so the bars are alone now, so we can split this into 2 different scenarios. So we have this 2x minus 3, that's greater than 5. But then we also have this 2x minus 3, and that's going to be less than negative 5. So make sure you write the opposite inequality symbol. So we switch this greater than to less than, and then instead of writing a 5, we wrote the opposite of 5. Okay, so let's go ahead and solve this now. We have 2 different things we have to look at. So let's go ahead and add 3 and add 3. If we go ahead and do that, then those 3's are going to cancel out. We'll have 2x is greater than 8. Then we can divide by 2 and divide by 2. So x would be greater than 4 in this one scenario. And then if we add 3 and add 3 to this one on the right, we're going to get 2x is going to be less than negative 2. And then we can divide by 2 and divide by 2 and see that x could be less than negative 1. So putting this together, we're going to say that x is greater than 4, or we can say x has to be less than negative 1, and that would be the final solution here. Those values would make this inequality true. And if we want to look at this on a graph here, I'm going to put that up here. So let's go ahead and put a number line, and we put a negative 1 maybe somewhere over here, 0 would be here, and then 4 would be somewhere to the right. And then we're saying that x has to be greater than 4, which is an open circle going to the right, or x is less than negative 1, that's an open circle to the left. That would be the graph here. All right, let's move on to part 2. In part 2, we're going to be talking about linear equations and functions. So for number 11, let's get started. It says find the slope of the line that goes through these 2 points here. Let's go ahead and call these x1 and y1. I'm going to call this one x2 and y2. So remember that slope is equal to the change of y divided by the change of x, or the ratio of the change of y to change of x. So let's see, for change of y, we could do y2 minus y1 and put that over x2 minus x1. And you could switch the 1's and 2's if you want, and that's fine. But we go ahead and substitute some values in here. We're going to see that this is going to be equal to negative 2 minus 3. That's y2 minus y1. And then x2 minus x1 is 6 minus negative 4. So negative 2 minus 3 is going to be negative 5. And then 6 minus negative 4 is going to be positive 10. Then we can go ahead and divide both sides, or top and bottom rather, by 5. And we're going to get negative 1/2. And that would be the slope. For number 12, we are going to write an equation of a line in point-slope form, given this point of negative 3, 1, and we have a slope of 4. So what is point-slope form again? That is going to be y minus y1 is equal to m times the quantity of x minus x1. All right, and so just to be clear here, this negative 3, 1 is going to be x1 and y1. So negative 3 is x1 and positive 1 is y1. And then on top of that, the slope here being 4, that's going to be this m. So we just have to substitute some values in. So we have y minus y1, so it's going to be minus 1, is equal to 4 times the quantity of x minus the negative 3. But if we do minus a negative, we can just write add a positive. And this right here would be the equation of the line that goes through that point with that slope. If you want to distribute the 4 and rewrite this into slope-intercept form, or y equals mx plus b, you could do that also, but it doesn't tell us to do that. For number 13, let's go ahead and see if we can find the x and the y intercepts for this graph here. So if we're going to go ahead and start with finding the x-intercept, right? The x-intercept when y is equal to 0. So that's going to happen when y is equal to 0. So let's go ahead and do that first. If we do that, we're going to get negative 6x plus 9 multiplied by 0. That's going to be equal to 72. So this will be negative 6x plus nothing is equal to 72. So we can drop that. And then we can go ahead and divide both sides by negative 6 and negative 6. So then if we do that, we see that x here is going to be equal to negative 12. So for our x-intercept, we're going to get negative 12 comma 0. All right, so that's going to be the x-intercept. Now, what about the y-intercept? For the y-intercept, this is when x is going to be equal to 0. All right, all y-intercepts occur when x is equal to 0. So if we do that, we're going to have this negative 6 multiplied by 0 plus 9y is equal to 72. Negative 6 times 0 will become just 0, so we have 9y equals 72. Then we can divide by 9 and divide by 9 and say that y is equal to 8. So that means the point 0, 8 is going to be the y-intercept here. So this right here will be our x-intercept. Remember, the x-intercepts always occur when y is 0, and this will be our y-intercept, which always occur when x is equal to 0. Here's number 14. For 14, we're going to write the linear equation of a line in standard form that goes through these 2 points of 3, negative 4 and 1, negative 6. Okay, so what is standard form? Just to remind you, standard form of a linear equation is going to be that form where we have that ax plus by is equal to c. Okay, where typically a, b, and c are whole numbers, not fractions, and a is a positive number. All right, so to get started, maybe let's see if we can find the slope first. So I'm going to go ahead and say that the slope, or m, that's going to be the change of y first. So I'm going to do negative 6 minus negative 4. This is very similar to number 11. So if you want to think back to how we did that one, that's fine. So that's the change of y. Over the change of x is going to be 1 minus 3. So if we do this, negative 6 minus negative 4 is going to be negative 2. And then 1 minus 3 is negative 2. So negative 2 divided by negative 2 is just positive 1. So that's the slope here. Then if we want to use point slope form, we can say y minus y1 is equal to m times the quantity of x minus x1. And for using point slope form, I think this makes a lot of sense because we have a point and we have a slope. So this 1 here we found, we can be using for m over here. And then for a point, you can either choose 3, negative 4 or 1, negative 6. I'm just going to go ahead and use 3, negative 4. And 3 will be x1 and the negative 4 will be y1. All right, so you can choose. Let's substitute that in. So we're going to have y minus negative 4, which is just y plus 4, is equal to 1. That's kind of nice, times the quantity of x minus 3. Okay, so this is in point slope form. We want in standard form. So let's go ahead and distribute this 1, which doesn't really change anything. So we have y plus 4 is equal to 1x, or just x, and then minus 3. Right now, we're still not in standard form. We need x and y to be on the same side here. Let's go ahead and take away y and take away y. If we do that, the y's on the left will cancel out. We get 4 is equal to x minus y minus 3. And let's go ahead and take this and move it to the side here because we're running out of space. So we have 4 is equal to x minus y minus 3. Now, if we want our constants to be on the same side, we have to go ahead and add 3 to both sides here. If we do that, then 4 plus 3 on the left is going to be 7. So 7 is equal to x minus y. So our standard form equation here is going to be x minus y is equal to 7, where a is 1, b is negative 1, and c is positive 7. This right here would be our equation written in standard form. Okay, let's take a look at 15. It says here that Benny must fetch his ball 48 times a day to stay in shape. He fetches the ball 4 times per minute. Write a linear equation in slope-intercept form to represent the amount of times Benny still has to fetch the ball after X minutes. Now, a key place to start here is that we're being asked to write an equation in slope-intercept form. So we want to remember that slope-intercept form is going to be that y is equal to mx plus b. Okay, so that's what we're looking for here. So this y that we have here is going to be how many Benny still has to pick up that's left. And then this m here, the slope, is going to be the rate at which he's going ahead and catching those. And then this is going to be the starting number that he has, right? So we're going to write y is equal to, or what he has left. And instead of writing 4x, let's write negative 4x, because he has 4 less balls to catch every minute if he's catching 4 every minute, right? So it's going down by 4 in total, and then plus 48, and that should be the total that he has to start with here. So I think this right here would be our linear equation. And if you want to see if this makes sense, if we make a quick table here, hopefully this will be a little bit more clear if that was confusing. If 0 minutes go by and x is 0, he still has 48 that he still has to catch. But what if 1 minute goes by? Well, 1 times negative 4 is negative 4. Negative 4 plus 48 means there's 44 left that he needs to catch. So on and so forth. If 2 minutes goes by, then he would have caught 8 balls, so then there's 40 left, etc., etc. So hopefully that makes sense that the amount he has left is going to be going down over time. So that's why we need a negative 4 for the slope. For number 16, we have here, we're going to write 3 linear equations that are parallel to this. The key word is parallel because that's going to tell us that we have to have the same slope here. Okay, so right now our equation is written in standard form, and we want to go ahead and turn it into slope-intercept form so we can find the slope. So that's that y equals mx plus b. So let's move the x's to the other side. If we do that, we're going to get negative 5y is equal to negative 3x plus 15. And then we can go ahead and divide both sides by negative 5 here, and divide this side by negative 5 as well. We're going to go ahead and get y is equal to, then negative 3 over negative 5 just becomes 3/5. And then 15 divided by negative 5 is a negative 3. So this would be the equation here for this line in slope-intercept form. And then this slope here, right? This is our slope. In order for equations to be parallel to it, they also have to have the same slope. So for example, one equation we could write would be y is equal to 3/5 x. And then we could write plus 7, right? So that would be a line that is parallel to the one we have there, but has a different y-intercept. Here's another one. We could write y equals 3/5 x minus 10, right? Or we could write something like y equals 3/5 x plus, I don't know, 3. Okay, so these would be 3 different examples of lines that are parallel. And the key feature is here that we just have to have the same slope. And that's all that really matters to get parallel lines. All right, for number 17, let's see here. We need to write 3 equations that are perpendicular to this equation that we have over here. So perpendicular is the key word here. So I'm gonna go ahead and review that in just a moment. But we need to, again, figure out the slope just like for parallel lines. So if we have negative 4x plus 2y is equal to 18. Let's see, we got to find out the slope first here, okay? I think actually what I'm going to do first is I notice that everything can be divisible by 2, so I'm just going to do that to get some smaller numbers. Feel free to do that if you notice things like that in the future. Negative 2x plus y is equal to 9, okay? At this point, let's go ahead and get that into y equals mx plus b form. All right, get that y alone. So I'm going to add 2x and add 2x. So I'm going to have y is equal to 2x plus 9. Okay, so what's the important thing here? The important thing is the slope. The slope here is going to be 2. So now that we know the slope is equal to 2, we want to remember that to get perpendicular lines, we have to go ahead and find out the slope that is going to be the opposite of what we currently have. And it also has to be the reciprocal. Reciprocal. Let me see if I can spell that. Reciprocal. I think that's right, okay? So the opposite reciprocal, the opposite of 2 is going to be negative 2, and the reciprocal is going to be 1 over 2. So we're going to go ahead and use the slope of m equals negative 1/2. Okay, so if we're going to go ahead and write 3 equations that are perpendicular, we can write y is equal to, I don't know, negative 1/2 x plus 5. We could write y is equal to negative 1/2 x and then write, I don't know, minus 8. and then y equals -1/2 x, and then plus 1. All right, so all of these would be perpendicular to that original equation because they have slopes that have the opposite reciprocal to the original equation. All right, cool. Let's check out number 18. For number 18, we're going to go ahead and graph a linear inequality and then state 3 ordered pairs that satisfy it. So we have this y is less than 3x minus 4. We're going to go ahead and graph this. Keep in mind that if we want to think about this as an equation first, we can think about this as just y is equal to 3x minus 4, where we know the slope is going to be 3 and the y-intercept is going to be -4. So just a rough sketch here, but if we go ahead and make an x-axis and then make a y-axis, something along the lines of this. Let's see, -4 would be somewhere over here, 1, 2, 3, 4. And so we're going to go ahead and plot that point down. That's -4. That's the y-intercept, or the b value. And the slope is 3, right? So we have to go up 3, up 1, 2, 3, and over 1. Go ahead and put a dot over there at this point right over here. And then if you take a look here, this is going to be a dotted line. So if you remember that when you graph these types of inequalities, you have to make sure you have either a dashed line or a solid line, right? So if we go ahead and graph this, then it's going to be dashed in this case. So our inequality is going to look something like this, our linear inequality. And I think that's about it, but we also have to do some shading, right? So we're either going to be shading on this side of the line or shading on this side of the line, right? In order to do that, we typically just test a point on one of the sides. So I'm going to go ahead and test, let's go ahead and test the point of 0, 0, right? Which is right over here. And if it works, then we're going to shade that side. If it doesn't work, we're going to shade the other side. So testing this, we're going to say 0 is maybe going to be less than this 3 times 0 minus 4. Let's see, 3 times 0 is 0, 0 minus 4 is -4, so is 0 less than -4? I don't think so, so that's not true. So since that is false, then 0, 0 doesn't work. That means that nothing on that side of the line will work, and we'll go ahead and shade everything on the other side. So what are some 3 points that you could go ahead and say work here? Anything that's over to the right, so maybe we can say like 7, -8. That would be somewhere that's, let's see, 1, 2, 3, 4, 5, 6, 7, 5, 6, 7, 8. So I don't know, that's maybe a dot that's over here. You can say something like 3, 0, which would be a dot that's like maybe somewhere right here on the x-axis. And then finally, something like, I don't know, 10, -15. So anything that's pretty far down in quadrant 4 will work out here. Here's number 19. For number 19, we're going to go ahead and graph the linear inequality here and state 3 ordered pairs that satisfy it. So again, we're going to do something very similar to number 18, but this time we have a little more work to do because this is more in standard form. It's not in that y equals mx plus b form. So just like in the last one, I'm going to think about this as an equation first. So 2x minus this 3y is less than or equal to 9. So this one here is very similar to number 18. It's just written in standard form instead. So just like the last problem, it's helpful to have it in slope-intercept form. So I'm going to think about this as an equation first. So 2x minus 3y is equal to 9. So I'm just going to rearrange this first before I go ahead and make this graph, right? So let's go ahead and get this into y equals mx plus b. So I'll take away 2x, take away 2x. If we do that, we're going to get -3y is equal to -2x plus 9. And then divide by -3 and divide by -3. We're going to get y is equal to positive 2/3 x and then -3. All right, so keep in mind here that we have this y is equal to this 2/3 x minus 3. But we have to be careful thinking about our inequality symbols, right? We did have a less than or equal to symbol here. So if we kept that here and kept that here, because we divided by negatives here, then we're actually going to have to flip that inequality. So while we do have this equal sign, keep in mind this was less than or equal to. So when we rewrite this, this is now going to be y is going to be greater than or equal to 2/3 x minus 3, all right? And so if that's confusing, feel free to just keep it as inequalities the whole time if that is something you prefer to do. We're gonna have here y is greater than or equal to 2/3 x, let's say 2/3 x, and then -3, Okay, so just be careful with that. But remember, when you divide by a negative, we're actually flipping the inequality symbol. And so that's why we're going to have a greater than symbol instead of a less than symbol. All right, so I think we have everything we need to graph here. So let's go ahead and make our x-axis and our y-axis. Alrighty, so there we have it. Rough sketch here, and then we have our y-intercept of -3. So there's -3. I'm going to go ahead and put a point right on the y-axis. And our slope is 2/3, so that means we have to go up 2, but then to the right 3. 1, 2, and then 1, 2, 3. Maybe something like right over here. And it looks like we're going to have a solid line here just because we have that or equal to. So putting a solid line through these would look something like this. Okay. Now, which side do we shade? Are we shading this top side of it, or are we shading the bottom side of it? I think I'm going to go ahead and just test 0, 0. That's above it, and if it works, we'll shade that side. So let's see here. If I test 0, 0, we're going to get 0 is greater than or equal to, maybe. The 2/3 multiplied by 0 minus 3. So 2/3 of 0 is 0. 0 minus 3 is -3. So is 0 greater than or equal to -3? Yeah, that's true. So when we go ahead and shade this, we're going to go ahead and just shade everything that's above this line. So what are 3 solutions that could work here? Well, we just tested 0, 0, so I feel like writing that one. We can also say something like 1, 0, that's definitely above the line, and then something like -8, 3, something over in quadrant 2 is definitely going to work as well. Here's number 20. For number 20, Benny has already eaten 9 treats. Each additional day he eats 4 more treats. Write the explicit and recursive formula representing the function. So we know Benny has already started off eating 9 of these treats, then each day he's eating 4 more, so 13 is going to be the next one, and plus 4 would be 17, plus 4 is going to be 21, plus 4, 25, and hopefully you kind of see the pattern here, but it looks like we're just going up by 4 each time. Now a sub 1 is just going to be the first number in this term, so a sub 1 is going to be 9 here, and then the difference between each of these, or the d value for difference, is going to be plus 4 each and every time. So for our explicit formula here, we want to try to remember that we have a sub n, which is any number in that sequence. That's going to be equal to a sub 1, or the first number in the sequence, plus d times the quantity of n minus 1. So this is kind of our formula for explicit, so maybe I can go ahead and highlight that to make that a little bit more clear. But the explicit is the one we're doing right now, and that's this formula over here. Right, so a sub n, that's just telling us any number in the sequence. A sub 1 is going to be the first number in the sequence. D is the common difference between each of them, which is plus 4 each and every time. And then n is, again, the number in the sequence, and then minus 1. So if we go ahead and substitute some values in here, a sub n, which is any particular number in the sequence, is a sub 1, which we said was going to be 9. That's the first number in the sequence, plus d, which is 4, times this n minus 1. So this right here would be our explicit formula. And if we wanted to go ahead and just see if this makes sense, we could try a couple quick examples. Let's just say n was equal to 1. If n was 1 and you want to find the first number in the sequence, then you would put a 1 here. 1 minus 1 is 0. 0 times 4 is still 0. So a sub 1 would equal 9 here, right? You can go ahead and write that on the side if you want. A sub 1 would equal 9. But what if we said we wanted to find a sub 2, or the second number in the pattern? Then n would be 2. You put a 2 here. 2 minus 1 is 1. 1 times 4 is 4. And 4 plus 9 would be 13. So we have then a sub 2, or the second number in the pattern, and that would be 13. And for good measure, what if we just wanted to find the fifth number in the pattern, a sub 5? You would plug in n equals 5 here. And so a sub 5, or the fifth number in the sequence, you do 5 minus 1 is 4. 4 times 4 is 16. 16 plus 9 would be 25. So the fifth number in the pattern here does happen to be 1, 2, 3, 4, 5. The fifth number is 25. And so you can use this formula to figure out any number in the sequence. Now, how about for the recursive formula? For recursive, this is helpful to find any number in the sequence as long as you have the previous term in there. So for the recursive here, let's go ahead and write this down. This would be a sub n. So any number in the sequence would be equal to the number in the sequence that's before it, or a sub n minus 1, and then it's going to be plus that common difference that we have here. So this right here would be our recursive formula. So this right here is our recursive formula, and that helps us find any number in the sequence as long as we have the one before it. So we can go ahead and say here that if we want to find any number in this pattern, a sub n, that's going to be a sub n minus 1, or the number before it, plus the common difference, and in this case we have 4. So that's going to be the common difference here. So this right here would be our recursive rule. So for example, if we just wanted to try a couple quick examples here as well, we can say, what if we wanted to find a particular number? So let's say a sub 4, or the fourth number in this sequence, a sub 4. Then we can go ahead and figure that out by just saying, okay, if we know the a sub 4, then we know n is equal to 4. Then this would be 4 minus 1, which would be 3. So this would be the third term. So that would be the third term here, which is 17. So 17 plus this 4, that would be 17 plus 4 is what, 21? And so that kind of matches here. So it's kind of intuitive, I think, when you think about it, because you're basically saying if you want to find this fourth one, then if you can take the third one and add the common difference of 4, you're going to get that 21. Similarly, if you take a sub 5 and you want to figure that out, then n would just be 5 here. So this would be a 5. And then that would be 5 minus 1 is 4. So a sub 4 would be the fourth number. But then if you add 4 on, you're going to get that 25, or the fifth number, right? So here you have just your explicit and recursive formula representing this arithmetic sequence. Alrighty, so that just about wraps up part 2. So let's now check out part 3, where we're going to start going over some systems of linear equations and linear inequalities. So for 21, we have the system here. The system has two linear equations, and it looks like they're written in standard form. What I'm going to do here is, I think I'm going to solve by elimination. So we have a few different methods to solve by. I'm going to eliminate the y terms. So I'm going to get these y coefficients to be 6, because that's the LCM of 2 and 3. So I'm going to multiply this top equation by 3. And this bottom equation by 2. All right, so if we go ahead and do that, the top equation is going to end up being 9x minus the 6y, and that's going to be equal to negative 27. And then for the bottom equation, 2 times 4 is going to be 8, so that's 8x plus 6y, and that's equal to 44. All right, so we have these two linear equations, the system here. To go ahead and eliminate the y terms, I'm going to go ahead and add these two equations together. Notice if we go ahead and add this negative 6y with this positive 6y, they're going to cancel out and become 0. So then those get eliminated, right? So 9x plus the 8x, that's going to get a 17x in the beginning here. The y's are going to get eliminated. And then negative 27 plus 44 is going to be positive 17. All right, finally, this is a one-step equation. We can go ahead and divide both sides by 17. If we go ahead and do that, then we find out that x is going to equal 1. All right, so we're not quite done, but that is along the right way. We should take this 1 that we just found and substitute it into either this top equation for x or the bottom equation. I'm going to go ahead and use the bottom equation just because we see here that there's no negatives in there at all. So I'm going to take this 1 and I'm going to go ahead and plug it in right over here. So that's going to be 4 multiplied by 1 plus 3y, and that's equal to 22. 4 times 1 is 4, so we have 4 plus 3y is equal to 22. Then we can go ahead and take away 4 and take away 4. If we go ahead and do that, we're going to get 3y is equal to this 18. And then finally, we can divide both sides by 3 here, and we see that y is equal to 6. So what's the solution for this system? There's going to be one solution, and it's going to be at 1, 6. That's the point at which these two linear equations are going to cross paths. For number 22, here we have 10 snacks and 12 drinks are going to cost $23. Then 5 snacks and 4 drinks are going to cost $10. So how much does 1 snack and 1 drink cost altogether? So let's start off by defining our variables. I'm going to start with x. That's going to represent the cost or the amount of money for a snack. Okay, and then I'm going to use the variable y to represent the cost of a drink. Okay, so the first scenario here is we're buying 10 of these snacks, so it's 10 times whatever the price of a snack is, plus 12 of these drinks, so 12 times whatever the cost of a drink is, and we know that's $23. That's our first linear equation. And then secondly, we have 5 snacks, so it's going to be 5x, plus 4 drinks, that's going to be 4y. and that's going to equal $10. So it looks like we have a system of linear equations here. And I'm going to go ahead and use elimination again, except this time I think I'm just going to leave the top equation alone, and I'm going to multiply the bottom equation by 2. In this case, I'm going to be eliminating the x's. So let's see what we're going to have here. We have 10x plus 12y is equal to 23. And then if we multiply the bottom equation by 2, we get 10x plus 8y is equal to 20. Okay, if we go ahead and just subtract these two equations, we're going to eliminate the x terms here. So the 10x minus 10x is 0x, 12y minus 8y is going to be 4y, and then 23 minus 20 is going to be 3. And then we can go ahead and just divide both sides by 4 here. And we find out that y is going to equal 3/4, or you can also say that y here is equal to 0.75. So that would be one of these drinks is going to cost 75 cents. Okay. Now let's go ahead and take this y equals 0.75 and either substitute in here or in here to solve for whatever x is, or the cost of a snack. Now what I'm going to do is I'm going to go ahead and plug it into the bottom equation just because their numbers are a little bit smaller. And so if we do that, we're going to have here, let's see, it's going to be 5x plus 4 times, it looks like 3/4 might be easier to do in our head. I'm going to use 3/4 instead of 0.75. So 3/4 of 4, that's going to be just 3. So we have 5x plus 3 is equal to 10. Take away 3, take away 3. That means that 5x is equal to 7. And then divide by 5 and divide by 5. So we can see here that x is going to be equal to 1 2/5, or that's going to be 1.40 if you convert it to a decimal. So what did we just find out? It says 1 snack and 1 drink. Let's go back to the beginning here and say that the snack here we just found out is going to be $1.40. That's for the cost of one of these snacks. And then for the drinks, it's going to cost 75 cents for each of these drinks. Alrighty, let's check out number 23. That's going to be right over here. So the total cost of admission to a Benny concert where he does tricks is $162 for 12 children and 3 adults on a Friday night concert. And the total cost for admission was $122 for 8 children and 3 adults, and that's for a Saturday concert. So how much was each of these tickets? So this one's very similar to the last one, where we can start writing our equations in standard form. And so let's see, let's have x maybe represent the total cost for the children. And let's use y to represent the total cost for an adult. So for our Friday night equation, we're going to say that there are going to be 12 of these children tickets. We don't know how much they cost yet. We're going to figure that out. Plus 3 of these adult tickets. We're going to say 3y. And that's going to be a total of 162, and that's for Friday's tickets. On Saturday, it was a little different though. Saturday, it was 8 children, so it's 8 times the cost of each of those tickets, plus 3 times the cost of the adult tickets, and that was $122 in total. So this is going to be our system. This one's actually really nice because we can use elimination and do it rather quickly. We can actually subtract right away if you notice that the coefficients for y's match already. So 12x minus 8x is going to be 4x. The y's get eliminated, and then we have 162 minus 122, which is just 40. Right? So that's kind of nice because we can just divide this really quickly and say that x, or just one of these tickets, is going to be equal to $10. So that's the cost of one of the children's tickets. Now we can take this 10, and that's what x is. We can either plug it in here or plug it in here to solve for y. I'm going to plug it into the bottom equation. Again, it has smaller numbers, so I'm just going to go ahead and use that one. So I'm going to plug in x right here. If we do that, that's going to be 8 multiplied by that 10 plus 3y, and that's equal to 122. 8 times 10 is 80, so we're going to have 80 plus 3y equals 122. Take away 80 from both sides of the equation. So we're going to get here that 3y is equal to 42. And then divide both sides by 3. We find out that one of these adult tickets is going to be $14. So not a lot more expensive, but a little bit more than what the children's ticket was. So we can go ahead and conclude that each of the children's ticket is going to be $10 here. All right, a little cheaper. And then the adult tickets are going to be $14 each. All right, here is number 24. For 24, we have a system. We could use elimination if we wanted to rearrange some things, but if you take a look here, we actually already have y isolated here. Y is equal to this negative 7 over 2x plus 11. So if we know y is equal to that, we could actually just take this entire expression on the right and substitute it in for y into the second equation. So I recommend using substitution in this case because one of the variables is already isolated. So let's go ahead and do that. I'm going to go ahead and take this negative 7 over 2x plus 11 and swap it in for this y value over here. So if I do that, it's going to say 7x plus 2 multiplied by this negative 7 over 2x plus 11, and then that's going to be equal to 20. Okay, so let's go ahead and distribute this 2 over here and distribute this 2 over here as well. 7x is going to stay the same here. The 2 and the 2 here are going to cross cancel when we do this first one, so these cross cancel. That's just going to be negative 7x, so instead of writing plus negative 7x, I'll just write minus 7x. And then if we go ahead and distribute this 2 over here to this 11, that's going to be 22, and that's equal to 20. Okay, let's go ahead and combine some like terms on the left side. So 7x minus 7x, that's actually 0x. So we're actually left with 22 is equal to 20, which we know can't be true, right? So that's not going to be a true statement. And so based on that, we're going to go ahead and say that for this linear system, there's actually no solution, which implies that if you were to graph these, they would be parallel to each other. They have the same slope. Alrighty, here is 25. For 25, we have another system. Let's see what's going on here. It looks like they are both in standard form here, just kind of written backwards a little bit. So let's go ahead and see if we can rearrange this so it's a little less messy. For this top equation, I'm going to go ahead and write it as negative 11x. I'm going to write in standard form, so put the x first, and then minus the 4y equals 36. And then for the bottom equation, let's just put the right on the left and the left on the right. So it'll be negative 10x and then minus 10y is equal to 20. All right, so at least it's more organized now. You can see that the x's are lined up on top of each other, the y's are lined up, and the constants are also lined up here, okay? And now while you can just solve this right away, I think I'm going to do a couple things to make my life a little bit easier, just my preference. I'm going to divide the top equation by negative 1. Okay, I'm going to flip everything just to make more positives. And I'm going to take the bottom equation and divide everything by negative 10, right? Because 10 is the GCF for the bottom equation. Totally optional, but I just prefer to work with some smaller numbers and more positive values. So for the top equation, everything's going to flip in terms of being the opposite. On the bottom equation, if we divide everything by negative 10, we're just going to get x plus y is equal to negative 2. So everything's a lot smaller and more positive, so in general I like this. You could rearrange the bottom one and use substitution, but I think I'm just going to use elimination here and just multiply the whole bottom equation multiplied by 4 and eliminate the y's. So we have 11x plus 4y is equal to negative 36 on top. I'm going to keep that the same. For the bottom equation, if we multiply everything by 4, we get 4x plus 4y is equal to negative 8. Then we just go ahead and subtract these two equations from each other. If we do that, 11x minus 4x is going to be 7x. And then negative 36 minus negative 8, that's just negative 36 plus 8. That's going to be negative 28. Then we can just go ahead and divide everything by 7 here. We find out that x is equal to negative 4. Okay, so we know what x is equal to. Now we just have to solve for y. It's up to you where you want to substitute it in. You could either take this negative 4 and plug it in over here, or plug it in over here to solve for y. Now for me, what am I going to do? I think I'm going to take this negative 4 and I'm just going to substitute it in right over here. And so if I do that, it's going to say negative 4y minus 11 times negative 4 is equal to 36. Now that's going to be negative 4y, negative 11 times negative 4 is positive 44. That's equal to 36. Take away 44 on both sides. Then we'll be left with negative 4y is equal to negative 8, and then divide both sides by negative 4. So then y equals positive 2. So for the solution here, the one point where these two lines are going to meet are going to be at negative 4 comma positive 2 over in quadrant 2, and that would be the solution to this system. All right, for number 26, we have another system here. This time it looks like we have some different types of fractions as well. So let's see how we can deal with this without making it too messy. First things first, for that top equation, I think what I'm going to do is divide everything by -4. Hopefully you'll see why in just a moment. And I'm also going to rearrange it at the same time. So I'm going to take that -8x and divide it by -4 first. That's going to be a positive 2x. Okay, and then I'm going to go ahead and take that -24 and divide it by -4. That's going to be a positive 6. So I'm going to so far have to keep that on the same side. And then finally, that's the left side, but on the right side, 12 divided by -4, that's going to be -3y. All right, so as long as you do the same thing to everything, we're just making it a little smaller, smaller values to work with at least. And then for the bottom equation, you could keep it like this, but if you also multiply everything by the LCD, which for this case would be 18, then we would have no fractions to deal with anymore. So let's go ahead and try that. So 18 multiplied by this 1, that's actually just going to be 18. Okay, and then plus, if you take this 18 and then multiply it by this 5/9, the 9 and 18 would cross cancel, and you just have a 2. 2 times 5 is going to be 10, so that's going to be 10y, and that's equal to, and then if you take this 18 and multiply by -7/18, the 18s would cross cancel, and you'll be left with -7x. Okay, so this is a little bit easier to work with, I think, because there's some smaller numbers and there's no fractions anymore either. All right, so I think we need to do some rearranging here. I'm not going to write the workout for this part, but if you put everything in standard form, so for this top equation, if we do this one first, let's go ahead and add 3y to both sides. So you would get 2x plus 3y. And then if you subtract 6 from both sides, you would have a -6 on the right side instead. Again, if you need to pause to rearrange that, that's fine. For this one over here, I'm going to go ahead and move the -7x to the left side, which will become a positive 7x. We'll keep the 10y where it is, and then let's subtract both sides by 18 to move the 18 to the other side and make it -18. So this would be our entire system here, and now you have everything lined up. We have all the x's on top of the x's, the y's on top of y's, and the constants. I don't think using substitution is going to be the best method here. I think elimination is probably going to be our go-to strategy. What do we want to get rid of, the x's or the y's? Doesn't really matter, it's up to you. Let's get rid of the x's. Let's multiply this whole top one by 7 and multiply the whole bottom one by 2. That way we get coefficients of 14. So we're going to get 14x plus 21y is equal to -42. And then we're going to get 14x plus 20y, and that's equal to -36. Okay, so we can eliminate the x's by subtracting. 21y minus 20y, this is really nice, is y is equal to, so we actually don't have any more steps to do there. And a -42 minus -36 is going to end up being a -6. All right, now that we know that y is equal to this -6, I'm going to go ahead and take that -6 and let's substitute it into this top equation, and let's solve for x. I'm going to avoid those fractions in the bottom equation. So if we go ahead and do that, that should be -24 minus 8x, and that should be equal to 12 multiplied by -6. 12 times -6 is -72, so we have -24 minus 8x is equal to -72. Then we go ahead and add 24 and add 24. If we go ahead and do that, we're going to see that we have -8x is equal to -48. And then we can go ahead and finally divide both sides by -8. And we end up with x equaling +6. So I think the solution here is going to be 6, -6 over in quadrant 4. This would be the only point at which these two straight lines are going to cross each other. All right, here is 27. For 27, it says the difference between two numbers is 3 and their sum is 13. Find the numbers. Okay, so this is a pretty classic systems word problem. So difference means we're subtracting. So let's call the numbers x and y maybe. So let's say the difference of them, x minus y, is equal to 3, but their sum is 13. So we can say x plus y, sum means you're adding, equals 13. So this would be a quick system that you could solve to find these numbers. You could use elimination. You could either use subtraction and get rid of the x's, or use addition and get rid of the y's. I'm going to use addition here, and so if we do that, x plus x is 2x, the negative y plus y gets eliminated, and then 3 plus 13 is 16. And so we have a pretty straightforward equation here, and you get that x is equal to 8. Okay, and then if you take that 8 and you plug it into either one, let's plug it into this bottom one here. If we do that, then it's going to be 8 plus y equals 13. So then if you take away 8, we see that y has to equal 5. So what are the two numbers here? The first number is going to be 8, and the second number is going to be 5. And it makes sense because 8 minus 5 is that 3, but 8 plus 5 equals that 13. All right, cool. Here is 28. For 28, Benny is flying to Hawaii for a vacation. On the way there, his plane averaged 158 kilometers per hour with a tailwind. That means the wind is going with him or blowing in the same direction as the plane. On the return trip, his plane averaged 112 kilometers per hour by flying in the same wind. But this time it would be a headwind, and that means he's going to be flying against it. Find the speed of the wind and the speed of the plane in still air. Okay, so let's see. Let's do an equation for going to Hawaii. And so we know the speed was 158 with a tailwind, which meant the wind was helping. So let's see. Let's call x the speed of the plane, or the plane speed. Okay, and then let's go ahead and label y as our wind speed. All right, so when Benny is going to Hawaii, looks like 158 is going to be with the tailwind, which is helping, right? The wind is blowing with it. So if you take the plane speed and you add the wind to help it, it's going to end up going a total of 158 kilometers per hour. But on the return trip, the plane's going slower, so the wind is not helping. It's actually going against it. So the wind is going to be subtracting from the speed. So take away the wind, and that should equal 112 kilometers per hour in total, right? So in the first case, the wind's helping, so you're adding it. But in the second case, the wind is going against the plane, so we're subtracting it. It's taking away from the overall speed. And then so this right here would be a nice, easy system that we could solve for this problem. All right, in this case, I feel like going ahead and subtracting these two equations. If we subtract, then the x's will be eliminated. Then y, take away a negative y, would be 2y. And then 158 minus 112 is going to be 46. Okay, if we go ahead and then take this equation and divide both sides by 2, we can see here that y would be equal to 23. So the wind speed here is going to be 23 kilometers per hour, right? That's how fast that the wind is going to be going. And then if we want to figure out how fast the plane is going, let's go ahead and take this 23 and maybe plug it in right in for y on this top equation. So we say x plus 23. If you add the wind, that's 158. But what if you take out the wind? If you take away that 23, we see here that x is going to equal 135. Okay, so what does that mean? That means that the plane speed is going at 135 kilometers per hour. That's with the wind. So if you add them, you get that 158. If you add this plus this, you get the 158. But when you're going against the wind, you have this speed minus the wind that is going against it. That should equal this 112. All right, here is 29. For 29, we have to graph the system of inequalities, then state two ordered pairs that satisfy the system. Okay, so if you want to think of these as equations, you can too. So these are kind of in that form of y equals mx plus b. If that helps you a little bit, that might help you graph it. But then remember that we do have to know where to shade our answers as well, and if we're putting dotted lines or solid lines, right? So I'm gonna go ahead and use this greenish color for this first inequality. Let's go ahead and make a quick sketch of a graph here. So here I'm gonna make my x-axis, and then here I'm gonna go ahead and make my y-axis. Maybe something like that. And it looks like our y-intercept here is going to be -3. So I'm going to go and plot -3, 1, 2, 3. So I'm going to plot my y-intercept right over there. And then it looks like our slope is 2, so that's 2 over 1. So we need to go up 2 and to the right 1, and that would be right over here. You could also say you could go down 2 and then to the left 1, and you could plot a point down here as well. Right? Because we have a less than or equal to symbol for inequality, this means that we're going to have a solid line going through these dots here. And so any point that's on this line would be a solution. Okay, so that's this first one. I'm also going to take that first equation and test to see where to shade for that one. So if we test here, let's see, if I go ahead and write that equation on the side and say y is less than or equal to this 2x minus 3. Let's test 0, 0, which would be right over here, and if it works, we would shade that side. So if we test 0, 0, it'll be 0 is less than or equal to 2 times 0 minus 3. 2 times 0 is 0 minus 3, so is 0 less than or equal to negative 3? That does not work, right? So that means we're going to be shading on the side of this line that's not where the 0, 0 lies. So any points that are on this side of the line, any ordered pairs, would make that inequality true. All right. What about the second one? So let's take a look at this inequality where it's y is less than negative 3x plus 4. Let's start with the plus 4. That means that's the y-intercept. So let's go up 1, 2, 3, and 4. Let's go ahead and put a dot here. This one is going to have a negative slope here, right? So the slope is negative 3. So that means we can go down 3 and to the right 1. So down 1, 2, 3 and to the right 1. I'm going to go ahead and put a point right here. And if you want, you can go down 3 and to the right again 1 point. So 1, 2, 3 and go over. So this would be, if we connect these, this would be the graph for this inequality. And notice how I'm putting a dashed line just because it's just a less than symbol. It's not a less than or equal to symbol. So this is a nice rough sketch, hopefully, for this linear inequality. And for this one, we should also test where to shade. So let's go ahead and test 0, 0 for this one. So if we test it, we're going to say, okay, well, y is less than negative 3x plus 4. Let's test 0, 0. Is 0 less than negative 3 times 0 plus 4? Well, negative 3 times 0 is 0 plus 4. So is 0 less than 4? The answer to that is yes, I hope. And so we're going to shade the side that does have 0, 0. So that's going to be this side of that line. All right, it's the same side as where 0, 0 lies. And we're looking for a region that got shaded 2 times. And so that region would be anywhere that's on this line down here. That's not on this line, so you can't pick a point that's on this line, but it's going to be in this purple area down here. All right, and it goes down forever. So any points that fall in this area is going to be a solution to the system. So maybe you can choose something like, I don't know, 1 comma negative 10. I think that would be down in that area. Or you could choose something like 0 comma negative 15. That looks like it'd be far down enough. And these would be 2 ordered pairs that I think would make this true. And you can plug them into both inequalities to check if they algebraically make sense, but they do because I just checked it. Alrighty, here is number 30. For number 30, we're going to graph the following function. We're going to write it as a piecewise function and then state the domain and range of this function. All right, well, first it's probably good to know what the parent function for absolute value functions looks like, and that's f of x is equal to the absolute value of x, right? That's just kind of like the default function. And when you graph it, you want to know a couple things about it. You just want to know, first of all, that it's going to have a mirrored reflection, a vertical mirror, and it's going to start at the origin, and the slope of it, or the, how it's kind of changing over time, is going to be a 1-to-1 ratio. So if you take a look here, let's go 1, 2, 3 here, 1, 2, 3 here, and then 1, 2, 3 here, and then 1, 2, 3 here. So if x is equal to 0, then y would also equal 0. But if x was 1, y would be 1. But if x was negative 1, then y would also be positive 1. If x is 2, y would be 2. If x is negative 2, y would still be 2. And so you can see here that if you look at the parent function, or the function of absolute values, that like when it doesn't have any transformations, it's just going to look like this v, okay? There's kind of like this invisible little 1 for the slope that's out in front here, and so that's why it's going up 1 over 1 for the slope, but it's also going down 1 over 1 over here as well, because the absolute value of negatives is just positives as well. So how does the impact of this 2, this minus 3, and this 5, what impact does that have on this graph? Well, this 3 over here, let's go ahead and label some of these things so we're very clear what's happening. This is going to be our new slope. You can think about it like that. It's going to change the rate at which it's changing by. The number inside here is going to be telling us that we're going to be moving to the right 3 units. And then this 5 is going to tell us that we're going to be moving up 5 units. Okay, so those numbers, those constants are going to be helping us with knowing where the graph is being translated to or moved to, left, right, up, or down. So if the original vertex here is at 0, 0, but it's being moved 3 to the right and up 5, so then we're going to say the new vertex must be 3 to the right from 0, which is 3, and then 5 up from 0, so it's going to be 3, 5. So that's going to be the new vertex. So if we're going to graph this whole thing, so let's actually label this is just the parent function. This is not the graph of what we're looking for. It's just to help us kind of understand what it looks like. Let's graph the actual function that we are trying to now. Okay, so if we take a look here, again, we said this was moving to the right 3 and up 5. So if this is where the vertex was originally, we have to go to the right 3 and then up 5 before we put our new one down. So let's go 1, 2, 3, and then 1, 2, 3, 4, 5. And let's go ahead and put our point of 3, 5. Whoops, I want to use this purple color, and that would be our new vertex. Okay, now our slope earlier was 1, so there's an invisible 1 here, which is why we went up 1 over 1, up 1 over 1. In this case, our slope is 2, so we're actually going to go up 2 and then over 1. So let's go ahead and put 1, 2, and then 1. So we have to go up 2 spaces and then to the right 1. We're going to go up 2 and to the right 1. So you're going to notice that our graph is going to have a steeper slope because 2 is bigger than 1. And so it's going to be rising this way. And then similarly, we're also going to go up 2 and to the left 1. And we're going to notice that we're going to have a graph that is going to look like this. So I kind of went over my work earlier, but this part of it actually has a negative slope of -2, and then this has a slope of +2. Just like how this one had a slope of +1 this way, but it had a slope of -1 going this way. So it's got kind of 2 parts here to this absolute value function. Alrighty, so now we have our graph. Let's now take a look at writing this as a piecewise function. When we do piecewise functions, we're basically just breaking the graph up into a couple pieces. So I'm going to start by dealing with this left side, or the part that's coming down here. Let's go ahead and just write a linear equation for just this part of it, okay? This one has a negative slope of 2, so m equals -2 when we're dealing with that part. And in a moment, we can also go ahead and do the right side. So on the right side, that's from here when the graph touches that bottom part and then goes up. You can see here that m is equal to +2 for that part. So let's break this absolute value function into 2 linear functions, one with a negative slope and one with a positive slope. We also know the vertex, this point at which these two are converging, this right here, is 3, 5. So we know that's a point that's on both of those. So we're going to use this point of 3, 5, and we're going to use this point of 3, 5. So we have a point and we have a slope. So we can go ahead and use point-slope form and write linear equations for each of these. So again, point-slope form is y minus y1 is equal to m times the quantity of x minus x1. And so substituting in, we're going to get y minus 5 is equal to -2 times x minus 3. Distribute that -2, we get y minus 5 is equal to -2x plus 6. And we can add 5 to both sides and say y is equal to -2x plus 11. Okay, for our second scenario, we have y minus y1 is equal to m times the quantity of x minus x1. That's just the formula. Then plugging in, we have y minus 5 is equal to +2 times the quantity of x minus this 3. Distributing that 2, we have y minus 5 is equal to 2x minus 6. Then adding 5 to both sides, we're going to get y is equal to 2x minus 1. Alrighty, so when the slope is -2, that's going to be this equation here. So this linear equation tells us what's happening from this point to this point. And this equation over here is telling us what's happening when we're going over here on the right side. So those are going to be our two kind of linear equations, but you have to limit them a little bit because they don't go on forever in both directions. They kind of have some parameters where they stop and then start doing the other function. So you can see here that when this one stops at this point down here, this one's going to start, and then it's going to start moving upwards after this one moved downwards. Now let's put these together and write a piecewise function. So we have f of x is equal to, or y is equal to, it's going to be negative 2x plus 11. That's what the graph is doing when what? When x is less than or equal to this positive 3, right? Once x becomes 3, what happens? Things start changing. And then so the slope becomes positive, so it's 2x minus 1, and that's when x is going to be greater than 3. Up to you if you want to go ahead and put less than or equal to, or greater than or equal to, or the same. That's going to be totally fine. But notice here we're just saying the domain of this first function here only exists to the left of when x is 3, but once x hits 3, then what's going to happen? Then the function is going to start doing this function over here and go up. So we just broke this into two. So we're basically saying y is equal to this when it's on the left side, and then we're also saying that y is equal to this on the right side of the function. If you want to write the domain of this, let's go ahead and do that together. So the domain of this function is all the possible x values. So you can just say x is equal to all real numbers, okay? That's basically just saying x can equal anything, because the graph is going to keep moving to the left forever and to the right forever. You can also write this as x is equal to all real using that fancy r, or you can also use interval notation, which you'll learn more in Algebra 2 and pre-calc, which is from negative infinity to positive infinity. Now what about the range? For the range of this function, what we're going to say for that one is this is the lowest point to the highest point of the graph. So notice if you see the lowest point of this graph, that's going to be right here. The lowest point is 5. The graph never goes below that, but the graphs do go up forever, right? They never stop going up. So for the range, we're going to say that the y value is going to be greater than or equal to 5. So 5 is the lowest point, but it could be higher. You could also then say, using interval notation, which is a little bit more advanced, you can say y can equal 5 or anything above. Okay, so I won't go into too much of that now, but if you start seeing that later, hopefully that makes more sense. So that's a domain and range for this function. Alrighty, let's go ahead and check out part 4, where we're going to deal with some exponents and exponential functions. All right, so for 31, we have this rational expression, or basically just a fraction. So we have this 12, and then we have x to the 4th times y to the 6th. That's going to be in the numerator. And then in the denominator, it looks like we have 8x to the 3rd power times y to the 1st power. I'm just going to put that y to the 1 just there, so it's a little bit more clear. And then let's go ahead and simplify this fraction. So if we have 12 over 8, we can divide those both by 4. 12 divided by 4 is going to be 3. And if we take that 8 on bottom and divide it by 4, we're going to get 2. Next, we're going to take a peek at the x, and we have x to the 4 over x to the 3. The shortcut for simplifying this is this: you can subtract their exponents. So 4 minus 3 is 1. So we're going to just go ahead and write x to the 1st power on top. I basically cross out 3 x's on bottom and cancel those out with 3 of the x's on top. And then finally, we have this y to the 6th over y to the 1. And basically, we can cross off 1 from the top and 1 to the bottom. So we have y to the 5th on top and no more y's on the bottom. So finally, we can just say this expression is going to be 3x, or 3 times x times y to the 5th power all over 2. And this would be our final expression. Or we could also write the 3 over 2 as a coefficient. So 3 over 2 times x times y to the 5th power. So either one of these is fine. And this is writing our expression, or our fraction, using positive exponents. For number 32, let's see what's going on here. We have a more complicated looking expression here. What we're going to do first is just rewrite this so we understand what's going on. Looks like on the top we have 2 times a to the 4th power times b to the negative 3rd power times c to the 0th power. That's all being raised to the 4th power. And then underneath this we have 24 a to the negative 3rd power, b to the negative 8th power, and then c to the negative 5th power. I think the first thing to notice here is this c to the 0th power here. That's just going to equal 1. So because c to the 0th power is equal to 1, we don't really need to write it anymore because we're just multiplying by 1. So just on the side here, I'm going to write c to the 0th power is equal to 1. And then so we don't really need to write that. Okay. Next, let's just go ahead and apply this exponent of 4 on the top to each of these bases. So this 4 means there's 4 of each of these different pieces being multiplied on the bottom here. So let's start off with this 2 to the 4th power. That's 2 times 2 times 2 times 2. So that's going to equal 16 on top. Okay. And then we're going to say there are 4 of these a to the 4th powers. So if there's 4 of those, that's going to make it a to the 16th power. The shortcut is you can just multiply those exponents together. And then finally, if we have b to the negative 3rd power, but we have 4 of those, then that's going to be negative 3 times 4. That's going to be b to the negative 12th power. Alrighty, so we basically just took the top and we took that 4 on top and said there's 4 of each of those pieces on the inside of the parentheses. Now on the bottom, I'm just going to copy down this 24, a to the negative 3, b to the negative 8th power, and c to the negative 5th power. Alright, next what I'm going to do, you have a couple of different strategies that you can go by, but I'm going to go by taking all of these bases with negative exponents and then move them so they become positive exponents. So for example, it's b to the negative 12th. We're going to move it down to the bottom to make it b to the positive 12th. We can take this a to the negative 3, b to the negative 8th power, and c to the negative 5th power and move all 3 of these up, and then they're going to have positive exponents. So you don't have to do it this way, but I'm going to. So let's leave that 16 alone because it doesn't have a negative exponent. And let's leave that 24 alone. The a to the 16th is also going to stay put because it has a positive exponent. But if we move that, let's see, that b to the negative 12th power down, it's going to become b to the positive 12th power. And then moving that a to the negative 3 up, it's going to be a to the positive 3. And then move that b to the negative 8, so it's b to the positive 8. And then moving that c up, it's going to be c to the positive 5th power. Alright, so we basically just move this b to the negative 12th, we move this a to the negative 3rd, b to the negative 8th, and c to the negative 5th, and now we have all positive exponents. So now let's go ahead and use some of our quotient rules here. Alright, so starting off, let's see, we can go with the coefficients here. We can divide these both by 8. So if we divide these both by 8, we're going to get 2 on top, and then we're going to get a 3 on bottom. Let's keep this fraction bar a little longer here. And then let's take a peek at our a's. It looks like our a to the 16th and a to the 3rd are being multiplied together. So we can add 16 and 3 to make that a to the 19th power. And then we can then take a peek at our bases of b, so b to the 8 and b to the 12. We can subtract those, and then we would get b to the negative 4th, or we can say that no more b's on top and just 4 b's on bottom. So that'll be b to the 4th power on the bottom. Again, there's 4 more b's on the bottom than there are on top. And then finally, that c couldn't really do too much here. That c is just going to hang out because it doesn't have any bases of c on the bottom, so that c to the 5th is going to stay on top. All right, so this would be our final expression. All right, for number 33, we have an exponential function, and we're going to be taking a look at it, which is right over here. It's f of x is equal to 3 times 2 to the x power. And we're going to find out what f of negative 3 is and f of 4 is. Then we'll state the domain and range. Okay, so let's start with finding f of negative 3. Let's go to look at our function and find f of negative 3. So negative 3 is going to go in for x basically, right? So it's going to be f of negative 3 is equal to 3 times 2 to the negative 3rd power. All right, so following the order of operations, we're not going to do 3 times 2. We're going to do 2 to the negative 3rd power first here. So 2 to the negative 3rd power, that's going to be the same thing as 2 to the 3rd power, but the reciprocal. So it's going to be 1 over 2 to the 3rd power if we want to write it using positive exponents. And then if we go ahead and say 2 to the 3rd power, that's going to be 2 times 2 times 2, which is 8. So we have 3 times 1 over 8. And so that's going to be equal to 3/8. Okay, so f of negative 3. So if x is negative 3, then the y value for this function would be 3/8. Next, let's take a look at f of 4. So now we're changing x to 4 here. So let's find f of 4. That's going to be 3 times 2. But instead of raising it to the negative 3rd power like we did earlier, we're going to raise it to the 4th power here. And so following the order of operations again, we have to do the exponent or the power first. So that's going to be 3 multiplied by 2 times 2 times 2 times 2. That's going to equal 16. So 3 times 16, and that's going to be equal to 48. So if x was 4, then y, or f of 4, would be equal to 48. All right, if we were to go ahead and graph this thing, it's an exponential function, so you got to try to think about what that would look like. So this would be maybe the y-axis, and then this would be the x-axis. All right, so if this is x and this is y, this is an exponential function, and because the base here is greater than 1, then we know it's going to be an exponential growth function. So just kind of like real quick as a rough sketch, we would have something that looks like this, right, where it's going to start off kind of slowly going up, and then it's going to go up faster and faster and faster. That's an exponential growth function. And if you take a look at this, it's going to move to the left forever. You can notice that's going to the left forever this way, and it's going to keep moving to the right eventually forever as well as you keep moving to positive x values. So if we figure out the domain here, now if you take a look at this graph, we can keep going to the left forever, and we can also keep going to the right forever. This is going to keep moving to the left and to the right. So for the domain, which is really telling us all the possible x values, which is left and right, we can say that x can equal all real numbers for exponential growth function, so it's going to the left and to the right forever. Or you could also use interval notation and say it goes to the left forever and goes to the right forever towards negative infinity and positive infinity. Now for the range, this one's a little bit different. All right, if we take a peek here and see the lowest point here, we're going to see that this is actually going to approach the x-axis, which is right over here, but it's never going to touch it. So that's called an asymptote or horizontal asymptote. So it's never going to touch 0. So we're going to say y is going to be greater than 0. Can't be equal to it for these exponential functions, okay? So y can't be 0, so we'll put a parentheses there, but it does go up forever in the other direction. So again, it's going to eventually get closer and closer to this y equals 0, but it can't touch it, and it's going to keep going up forever on this side here. All right, here is 34. For 34, we have to go ahead and take a look at this exponential function, determine f of 0, then f of -4, and determine the domain and range again. So let's start with maybe identifying this f of 0. Okay, so f of 0, we're going to do that as changing x to 0. That's going to be 9 multiplied by 1/3 raised to the 0th power. Now if we do the power first, that's 1/3 to the 0th power, but anything to the 0th power is just 1, so this is really just 9 times 1, so that's equal to 9. All right, so if x was 0 here, then y, or f of 0, would be equal to 9. Now what about f of -4? Let's see here. If we say f of -4, that's going to equal 9 times 1/3 raised to the -4th power. Okay, let's see. Let's use that power first. If we do this 1/3 to the -4th power, keep in mind that the -4 power means we can just reciprocate the base. So this is going to be 9, and then it's going to be times this 3 over 1 raised to the 4th power, which is really just 9 times 3 to the 4th power. Now what's 3 to the 4th power? That's 3 times 3 times 3 times 3. That's going to be 81. Now 81 times 9, that's going to equal 729. All right, so if x was equal to -4, then this function would be at a y value of 729. Now a little different than the last problem, we can see here that the base of this power is less than 1, but greater than 0, so we know that this is actually an exponential decay function. So if you wanted to see what this graph would look like, very rough sketch here. Here's the y-axis, here is the x-axis. Then if we were to graph this thing, as we go towards the right, it would go down slower and slower and slower. And if we move to the left, it's going to go up and up and up faster and faster and faster. Okay, so if we go ahead and figure out what the domain here, the domain, again, this is all the possible x values for this function. We would say for these exponential growth and decay, that x is all real numbers, because you can see it goes to the left and right forever. You can also say it goes to -infinity on the left and it goes to positive infinity on the right for the domain. Now for the range, it's very similar to the last one as well. So the range here, you're going to notice that as we move down, this graph is going to get closer and closer and closer to the x-axis, but again, there's a horizontal asymptote, so y has to be greater than 0. It is going to go up forever, so if you look on the left side of this graph, as x approaches negative infinity, the f of x or the y values are going to approach positive infinity. All right, so we're going to say that the y values have to be greater than 0, or this function goes from 0 to positive infinity, where 0 is kind of the floor, and there's no ceiling, it just goes up forever as you go to the left. All right, cool. Here is 35. All right, the question is does the following function represent an exponential growth or an exponential decay function? All right, so let's look at the model of what an exponential growth or decay function looks like. It's going to be f of x is equal to a multiplied by b to the x power. That's kind of that general form. And so what we need to look at here is what is this 1/2 doing? That's this b value, right? So just to refresh your memory, if b is in between 0 and 1, then we know this is going to be a decay function, because if you raise anything that's a proper fraction to an exponent or positive exponent, it's going to get smaller and smaller and smaller. On the other hand, if b is greater than 1, or the base is greater than 1, that means any number that's improper fraction or higher, if you raise it to positive exponents, it's going to get bigger and bigger and bigger, right? So in this case, because we have b equals 1/2 in this particular exponential function, that is going to fall in between 0 and 1. So we know that this is going to be a decay function. So let's just go ahead and write that. This is a decay. All right, so this is going to be a decay function, because if you keep raising 1/2 to higher and higher powers, it's just going to become smaller. And so if you want to look at this as a rough sketch, here is our x-axis, here is our y-axis. That 80 really just tells you your y-intercept, so 80 maybe just say is over here along the y-axis, and then it's going to go down by half every time x becomes a higher exponent by 1. All right, here is 36. For 36, we have an exponential equation. When you're dealing with these types of equations, what our goal here really is to get these bases to be the same. So notice how on the left we have a base of 1/16, and on the right we have a base of 1/4. And when we deal with these, we really want to try to see if we can make the bases smaller generally. And so how can we make these smaller? Well, 16 is a bigger number and 4 is a smaller number. So maybe we could rewrite this one on the left and say this is going to be 1 over 4 to the second power. Do you agree that's equal to 16? I hope so. And so we can rewrite that as 4 squared. And then if we look to the right, we still have this 1 over, and this is 4 to the first power technically, right? I'm just going to write the 1 so it's extra clear. And then so this would be the same thing. So it's not quite perfect yet. However, if we take a look and try to deal with this, instead of writing 1 over 4 to the second power, remember our exponent rules, we can just say this is going to be 4 to the negative second power, right? I know it's a little strange because we typically try to turn negative exponents into positive, but you can also turn positive exponents into negatives if you use the reciprocals. And then on the right side, let's do a similar little process here. So 1 over 4 to the positive first power is the same thing as 4 to the negative first power if we put it in the numerator, and then it's going to be to the x plus 1 power. Okay, so using your power of a power rule, hopefully you can remember that you may, as a shortcut, multiply these two exponents together. So if we go ahead and do that, we can multiply this -2 by this x plus 3 and distribute it. So we can go ahead and take this -2 and multiply by both of these. So if we do that, we're going to get 4 to the -2x minus 6 is equal to, and similarly on the right side of the equation, this -1 can multiply by this x plus 1. So let's go ahead and distribute that -1 to both of those. And we're going to get 4 to the -x minus 1 power. All right. Now, if on the left side, we see here that we have this 4 and a 4 as a base, then if you raise it to this power, in order for this equation to be true, this exponent has to match this exponent, right? That's the only thing that would make sense. So if we go ahead and just set this -2x minus 6 equal to this -x minus 1, we're going to say it's going to be -2x minus 6 is equal to -x minus 1. Now, just using some little properties of equality, if we add 1x and add 1x to both sides of this equation, we're going to see here that the x's on the right cancel out. We're going to get -x minus 6 is equal to -1. Then we can go ahead and use another property of equality and add 6 to both sides. If we do that, the 6's will cancel out on the left side. We're going to get negative x is equal to positive 5. And then finally, we can divide both sides by -1 or multiply both sides by -1, your choice. So then we're going to find out here that x is going to equal -5. So there would be our solution to this exponential equation. Alrighty, here is number 37. For 37, we have another exponential equation here. All right, so starting off, I just want to copy down this problem so it's a little bit easier for me to work with. So we have 6 to the x power, that's being raised to the 1/3 power, and then this is all on top of 6 to the 2/3 power, and this is equal to 36. All right, so first thing I want to notice here is we have a power to a power property on top, so we can go ahead and just as a shortcut multiply these two exponents together. So if we go ahead and do that, we're going to have 6 raised to the x over 3 power, because x times a third is just x over 3. And this will be on top of 6 to the 2/3 power, and this is equal to 36. All right. The next thing we want to notice is that we have common bases here of 6 and 6, so we can go ahead and use one of our quotient properties. And if we do that, basically what we can do is take these two exponents and subtract each other, subtract the bottom one from the top one rather. Okay, so we can go ahead and rewrite this as 6 to the, and then let's go ahead and take these exponents of x to the 3 and 2 over 3 and say that is going to be x over 3 minus 2 over 3. Okay, so that's going to use one of our quotient properties of exponents. So you can see here that we kept these exponents the same for now. We just go ahead and write them as a difference, and we can see that we kept the base here the same as 6. Now on the right side, if you notice this 36, because we're dealing with exponential equations here, we should really try to see if we can get common bases. Just so happens that 36 is also 6 to the 2nd power, so we can also rewrite it that way, and so we have common bases here. All right. Now if we have common bases of 6, that means that this exponent that's on the left side, this exponent has to equal this exponent in order for this equation to be true. So we can go ahead and write the equation here of x over 3 minus this 2 over 3 is equal to 2. Alrighty. Now on the left side of the equation, we can go ahead and write this as one fraction because they have common denominators. So we have x minus 2 over 3, and that's equal to 2, but I'm going to write it as 2 over 1. All right. Now if you want to go ahead and use cross products here, you can. So you can multiply these diagonals. And we should be able to write an equation without fractions here. So 1 times x minus 2 is just going to be x minus 2. And then on the right side, 3 times 2 is equal to 6. Finally, we have this one-step equation. We can go ahead and add 2 to both sides here and say that x is going to equal 8. So that would be the solution. All right, here is number 38. For this one, Benny is going to invest $5,000 at an interest rate of 4%. This is going to be compounded quarterly. How much is the investment going to be worth at the end of 3 years? So this is a compound interest or an exponential application. A formula that we're going to want to know is the compound interest formula. So the account balance, that's going to be equal to the principal, or how much we start with, multiplied by 1 or 100% of it, plus R, the interest rate as a decimal, over n, the number of times it's compounded in a year, raised to the nt power, where t is time measured in years. Okay, so we're looking for A, and so what do we know? Well, the P here, I'm going to go ahead and highlight a few things. So we're going to start with this 5,000, that's going to be P. Okay, then we're going to say this 4%, that's going to be R, but we have to write it as a decimal. Then we have this quarterly, that's telling us it's 4 times a year. And then we also know that this n is going to be that same thing. And then finally, when it says 3 years, that means that t is going to be that 3. All right, so let's go ahead and plug some stuff in here. I'll use the different colors as well. So we have 5,000 that's being plugged in here. That's what we start with, multiplied by 100% plus, and then the R, or the interest rate here, is going to be 0.04. And that's over, well, it's being splitted into 4. So n is going to equal 4 here. And let's raise that to the nt power, which is going to be 4 multiplied by t, which happens to be 3. If we go ahead and simplify this just a little bit here, we're going to have this 5,000 in front, or the initial balance of this account. Then if we go ahead and figure out what 0.04 divided by 4 is, that's 0.01. plus 1. So this is going to be 1.01 and raised to the what? Well, it's 4 times 3, so it's being compounded a total of 12 times because it's 4 times a year for 3 years. That's 12 total compounding intervals. And notice how this is our b value, and we said earlier if b is greater than 1, it's an exponential growth function, so it's growing at 1% for every quarter. And so we can just take this exponential function and plug it into the calculator. We're going to find out this is going to be an approximation. I think this is going to be 5,803.77. All right, so in 3 years, if we have this interest rate and we start with $5,000, we're talking about $5,803.77. So that's the new account balance because it grew over time. All right, here's 39. For 39, we're going to take this radical and go ahead and try to simplify it. So a nice little trick you can do is use factor trees if that's something that can be helpful to you. So we're looking for perfect squares because this is square root. So 80, I'm going to say is 8 times 10. 10, I'm going to say is 2 times 5. 8, I'm going to say is 2 times 4. And then 4, I'm going to say is 2 times 2. So we have our prime factorization here. The reason why this is helpful is every time you can pair up 2 identical prime factors, that makes a perfect square that is useful. So notice this 2 and 2, that makes you 4, which is a perfect square, right? But then you can also notice here that we have another pair of 2, so 2 times 2, that's going to be another 4. Right? And then finally we have one more prime factor here, which is just 5. And the 5 can't do anything, so we're just going to leave it like this. So 80 is equal to the square root of 4 times 4 times 5, and hopefully that makes sense because 4 times 4 is 16, 16 times 5 is 80. But you can also go ahead and break this up into 3 different radicals, right? Because if you're multiplying radicals, you can always split it up as a product of these different bases. So square root of 4 times the square root of 4 times the square root of 5. And again, I'm doing this in kind of a long way here, but hopefully you can do this faster later on. Square root of 4 is 2, square root of 4 is 2, square root of 5 is irrational, so we're going to keep that the same. 2 times 2 is 4, so that's going to be 4 root 5. In the future, if you notice right away that 16 is a factor of 80 and it's a perfect square, you can go straight to this. Maybe you were able to do that. And so this would be 4 times the square root of 5. But hopefully prime factorizations can help you if you're having trouble finding those perfect square factors. All right, here's number 40. This one's going to be kind of similar to 39, but this time we have variables. So I'm going to go ahead and use that factor tree again, if that's helpful. Again, if you can do it faster, go ahead. I'm going to start with maybe 2 times 36, and then I'm going to go ahead. Oh, 36 is a perfect square, so that's kind of nice. 2 times 18, and 18 is going to be 2 times 9. And then 9 we can say is going to be 3 times 3. Alrighty, so let's see, do we have any pairs? Well, we have 2 and 2, which means we have a 4 here, right? So we have 4. And then we can say we have a 3 and a 3, and that's going to make 9. So let's multiply that by 9. And then I think we just have a 2 left over, so this leftover 2, I'm going to go ahead and put last. So the square root of 72 can be broken up into these 3 factors. And so we can also say this is equal to the product of these smaller pieces. So we have the square root of 4 times the square root of 9 times the square root of 2. Now square root of 4 is just 2. Square root of 9 is 3. And then the square root of 2 is irrational, so we keep it the same. 2 times 3 is 6, so we have 6 root 2. Alrighty, so that's basically helping us get started with at least the 72 part. All right, so we just started off and we dealt with this 72. We know the square root of 72 is 6 root 2. Now dealing with this x to the 4th power, if we go ahead and take the square root of x to the 4th power, we can say that's the same thing as the square root of x squared times the square root of x squared. If we separate 2 plus 2, that's 4. The square root of x squared is going to be x times the other square root of x squared, which is x. X times x is x squared. Okay, the shortcut is just take half of this even exponent, and that will work as well. And then finally, let's take a look at the base of y. If we look at this base of y to the 7th power, so let's break this up. We have y raised to the 7th power. This one is not a perfect square, but we can break this up into y to the 2nd times y to the 2nd times y to the 2nd times just a regular y at the end here, right? So if you take a look here, I just broke it up into perfect squares. So squared, 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 that's 6 of them, and there's an invisible 1 to make 7 of them. Now what is the square root of y squared? That's y times another y times another y times the square root of y. That one's not a perfect square. And so this becomes y to the third power on the outside times the square root of y. So putting this all together, that's the coefficient. This is our new x after we square root it, and this is our new y after we square root it. So finally, if we're putting this all together, our expression is going to be what's on the outside, but we do have a 6 that goes on the outside. We do have an x squared, that was a perfect square. We also have this y to the third power that got to come out. And then there's a few things that didn't get to come out of the square root just because they weren't perfect squares. So again, this came out, this came out, and this came out. So what's left inside, we just have a 2 and a y. So that 2 is going to go inside there, and then that y is also going to go inside there. So this would be a simplified version of this radical that we had. Alrighty, so that just about wraps up part 4. So let's check out part 5, where we are going to take a look at some polynomials and factoring together. So for number 41, we're going to go ahead and find the sum of these polynomials. And since we're adding here, we can just go ahead and add like terms. So we are going to go ahead and just start by looking at like terms here. If we have this negative 4x squared and this positive 3x squared, we're going to combine those to make negative 1x squared. Negative 1x squared. I'm going to put that negative 1 for now. Feel free not to. And then this negative 3x can be combined with this negative 8x. So if we combine those, it's just going to be adding, let's see, it's going to be adding a negative 11x. And then finally, we have these constants of a positive 7 and a negative 5. If we combine those together, we're going to get a positive 2. All right, so going ahead and just simplifying this, we can drop that negative 1 in front and just write negative x squared. And then instead of writing plus negative 11x, we could write minus 11x and then plus 2. So when we're adding polynomials, we can just go ahead and just drop those parentheses and just combine like terms. If you're subtracting, make sure you distribute that negative or that minus sign to all the terms in the second polynomial. All right, here is 42. For 42, we're going to go ahead and find the product, which means we're multiplying these two binomials together. They both have 2 terms. So first, this 3x is going to be distributed to this 2x. So 3x multiplied by that 2x is going to be 6x to the second power. Then you take this 3x and then distribute it to this positive 3. 3x times 3 is going to be a positive 9x. After that, this negative 5 is going to distribute to this positive 2x. So negative 5 times 2 is going to be a negative 10x. And then finally, this negative 5 is going to distribute to this positive 3. So negative 5 times positive 3 is negative 15. All right, finally, we're just going to go ahead and see if we have like terms. It looks like in the middle, we have this positive 9x and negative 10x. And if you combine those, we're going to have 6x to the second power minus 1x, or just minus x, and then minus 15. So if you go ahead and multiply these two binomials together, we're actually going to get this quadratic trinomial. All right, so that's the product here. All right, for number 43, we're going to go ahead and find the product again, but this time we're multiplying a trinomial by a binomial, and it's a quadratic times a linear, so we should end up with a cubic function or cubic expression at the end. So first, let's distribute this 3x squared to this 2x. Multiplying them together, we're going to get 6x to the third power. Then we're going to multiply this 3x squared by this minus 3. That's going to get us negative 9x to the second power. Now we're done with that 3x squared. Let's move on to the 5x. So 5x multiplied by 2x, that's going to be 10x to the second power. Then we can multiply this 5x by this negative 3. That's going to get us minus 15x. Finally, we have this negative 5. Negative 5 times this 2x is going to be a negative 10x. And then finally, this negative 5 multiplying by this negative 3 is going to be a positive 15. Now just going ahead and looking for some like terms, this 6x to the third power, this has no like terms. We're just going to leave that alone as 6x to the third power, has no like terms there. Then we have this negative 9x to the second power. That one can be combined with this positive 10x to the second power. If we do that, it's going to be a positive 1x to the second power, or just x to the second power. Then we're going to go ahead and have this negative 15x and this negative 10x. If we combine those, that's going to be negative 25x. And then finally, we have this constant at the end here. This plus 15 didn't really have any like terms. We're just going to write plus 15. All right, so our highest degree is 3, meaning this is a cubic polynomial. And so that makes sense because quadratics multiplied by linears gets you cubics. Here's 44. For number 44, we're going to go ahead and subtract these two polynomials from each other. It's kind of similar to 41, but a little bit different. The reason why it's different is we have to make sure we distribute this minus sign because there's technically a -1 in front of the parentheses, and that -1 needs to distribute to all of these because we're subtracting all of them. So if we go ahead and rewrite this, we actually don't have to do anything with the first polynomial, so 3x squared minus 5x plus 6. But then we're minusing this 8x squared, so minus 8x squared. We're subtracting a -9x, so it becomes plus 9x. And then we're taking away 10, so we have to write minus 10. All right, so let's go ahead and try combining some like terms. So this 3x to the second power and this minus 8x to the second power, those are like terms. If we combine those, that's going to be -5x to the second power. Then we can go ahead and see what else we can combine here. We have this minus 5x and this plus 9x. So -5 plus 9 is going to be a positive 4. So we're going to go ahead and write plus, and we have this 4x. And then it looks like we do have some constants here. So if we take this plus 6 and this minus 10, if we go ahead and combine those together, 6 minus 10 is going to be a -4. So we can go ahead and write minus 4 here. All right, and then just kind of simplifying this a bit, we have -5x to the second power plus this 4x. And then instead of writing plus -4, we can also just write -4. All right, so this would be our difference, or the answer to a subtraction problem for these two polynomials. All right, for 45, we're going to go ahead and find the value for c that makes this expression here a perfect square trinomial, right? So we have to go ahead and complete the square. So that's basically what we're doing. And so if we have this x squared plus 8x, and you're trying to find out what we're going to add on after this to make this a perfect square, what you do is you take a look at this value right over here. That's this number. This is, we call this b, right? So if we just take this 8 and we take half of it, or divide it by 2, and then we square it, that gives us that c term each time. This is called completing the square. You always take the coefficient for x, take half of it, and then square it. So half of 8 is going to be 4. 4 squared, that's going to equal 16. So 16 is going to be the value for c. That would complete this square. So c equals 16. If you want to see what this visually looks like of why we do that, you can go ahead and see here that if we have, let's see if I can draw this well. If we had a giant square, that this would be a completed square. And then we go ahead and break it up into a smaller square and some rectangles. So maybe something like this, right? Then if we were to say that this length from here to here is x, and this length from here to here is also x, then the area for this square would be x squared. And that's denoted over here by this x squared that we had in the problem, right? Now, what about the 8x? Well, if we go ahead and say that we have half of that, so if we go ahead and say that this is going to be a length of 4 here, and this is going to be the same length of that, that's going to be a 4 here. So if we go ahead and say this whole length is x plus 4 and this is x plus 4, then what if you wanted to find the area of this rectangle here? Well, it would be 4 multiplied by x to get the area of that rectangle. And so that area here would be 4x. And that means this area of this rectangle would also be 4x, just because if this is 4 and this is x, multiplying the length and width, we do get 4x. Okay, so if you see here, we actually have this x squared, which is this x squared here. And then we have this 4x, that's the area of this rectangle, and the area of this rectangle. So 4x plus 4x gets you this 8x that you can see over here. And those 4s are really half of the 8. So hopefully that makes sense. That we take half of it because there's 2 of the same rectangles. So the question always is, when we complete the square, is what are we doing with this area over here, or this little square? That's what we're doing when we're completing the square, right? So what's the length of this side and this side? Well, if this side is 4, then this side also is going to be 4. So if we go ahead and write that in, then if this is a 4 by 4 square, then the area of this piece that was missing, that we needed to complete the square, is that 16. And so if you go ahead and take this x plus 4 multiplied by x plus 4, we get x squared plus 8x plus 16. So you could write it out left to right as well as x plus 4 times x plus 4. But you can see that that's really just a square, so it's x plus 4 squared. So that's why it's called completing the square. For number 46, we're going to go ahead and find the product and then name this special case polynomial once we do that. All right, let's start by distributing this x by this x. So x times x, that's x to the second power. Let's take this x and distribute it also to this minus 4. So that's going to be minus 4x. After that, we're going to take this 4 multiplied by x, and that's going to be a plus 4x. And then finally, we're going to take this 4 multiplied by this negative 4. That's going to be negative 16. All right, in the middle here, let's go ahead and combine these like terms. And whenever you have this pattern, this is always going to happen. So if you ever see this where we have the same terms in both of these, but one has a plus and one has a minus, then the middle two terms will always cancel out to make 0. So we just have x squared minus 16. So this would be the product. And this special case polynomial, so I know we're supposed to write what the name of this special case polynomial is, and this is called the difference of squares. Difference because we are subtracting, right? This is a subtraction sign here, and squares because x squared is a perfect square and 16 is a perfect square. So it's a difference of perfect squares. Here's 47. For 47, let's go ahead and find the product and then state the name of this special case polynomial. So this one's actually pretty similar. Hopefully you notice the pattern that we have two identical terms, except one has a negative term second and one has a positive term second. So let's go ahead and do the same type of strategy. Let's take this 3x and distribute to this 3x. That's going to be 9x to the second power. Then take this 3x and then multiply it by this minus 5. That's going to be minus 15x. And then surprise, surprise, see what's going to happen here. If we take this 5 and distribute it to this positive 3x, that's going to be plus 15x. And then finally, this 5 multiplied by this minus 5 is going to be negative 25. Okay, so just like last time, we're going to notice here that we have two terms in the middle that can be canceled out to make 0. So we get this 9x to the second power minus 25. This right here is the product. And notice here that we only have two terms here, and this always happens when we have this difference of squares pattern. So I'm actually going to go back up here. Instead of going ahead and rewriting it, let's go ahead and take this and just write it over here. All right, for number 48, we're actually going to have a polynomial and we are being told to factor it. And so you want to take a look here at this pattern. And this pattern that we have here looks like just the two problems that we just previously did, right? So if you take a peek, this right here is a perfect square and this is also a perfect square. So this kind of fits that form of difference of squares where we have that pattern of a squared minus b squared, right? So you have a perfect square minus a perfect square, and that's always going to factor into the sum of their square roots multiplied by the difference of their square roots. So that's like the general pattern for perfect squares, or difference of perfect squares rather. So in this case, what are we going to say? We're going to say that this 4x squared, we're going to call that our a squared, and then we're going to take a look at this 49 and we're going to call this our b squared. All right, so we have our a squared minus b squared. So if we are saying here that a squared is equal to 4x squared, then we can also go ahead and take the square root of both sides and then say that a is equal to 2x, right? On that same thought there, if we're saying that b squared is equal to this 49, then we should be allowed to take the square root of both sides here and say that b is equal to 7. So if that's true, we should be able to go ahead and factor this, and we know that the pattern for a squared minus b squared is going to be a and a in the beginning here, then there's going to be a plus, and then there's going to be a minus, and then there's going to be a b and a b. But now we know what a is equal to. These a's are just equal to 2x, and then these b's here are equal to 7. So rewriting this with the actual values here, we're going to go ahead and write our binomials, and we're going to have 2x and 2x. Then because we have a difference of squares, one's plus, one's minus, and then we're going to go ahead and put a 7 here and a 7 here. So this looks hopefully familiar with the last two problems, but we have two terms that are the same. One has a plus and one has a minus as the operation. And so you can see here that the first term is just the square root of this, and then the second term of each binomial is just the square root of this. So this right here would be our factored form for this polynomial. Here's 49. For 49, we're going to go ahead and factor this special case polynomial. This one is interesting, and so the reason why that is because this first term here, this one is a perfect square. So this one is, if we take a look at the 16x squared, if you take the square root of it, you're going to notice that the square root of 16 is 4, and then the square root of x squared is just x. All right, so that's a perfect square. And the reason why we're going to keep on going and saying why this is special is because you can see the last term here, this one also happens to be a perfect square. So if we take this 81 and we take the square root of it, then we're going to see that that's equal to 9. So if you have this case where you have a perfect square in the beginning and a perfect square at the end, so this had a perfect square, this is a square root, this is also a perfect square. If you multiply these two together, you're going to get 36x. Right? And if you double this 36 and you get the middle term here, or the coefficient of 72, then this is called a perfect square trinomial. So for example, if we had the pattern of a squared minus 2ab plus b squared, where we have a perfect square at the beginning and at the end, this is always going to factor into the quantity of a minus b, and then another identical binomial of a minus b again. You can see if you distribute or FOIL this out, a times a is a squared, a times minus b is minus ab, then we have another minus ab, so that's why we have minus 2ab, because they have like terms, and then a negative b and a negative b make the positive b squared. All right, so in this particular problem, we can see that we know that a squared is equal to this 16x squared. We just said that a moment ago, and then we found the square root and said a was equal to 4x. And then what we did with that b squared, we said b squared was equal to 81, and then we said the square root, so we said b was equal to 9. All right, so if that's the case, then we should be able to say we know what a and b are. So here's a and here's b. Then we can go ahead and just substitute them in to this expression here. So let's go ahead and do that. If we go ahead and open up these parentheses, we know we're going to have 4x and 4x at the beginning here. And we know we're going to have 9 and 9 here. And we're going to have these minus signs because we need to get the negative 72 in the middle. So if you go ahead and write this, you can also combine this and just say, oh, this is going to be the quantity of this 4x. And then we have this minus 9. And we can also just say that this is squared because there are two of them. So this right here would probably be the most simple way to write it, but you can write it long ways too and just have two of the identical binomials. Notice here that if we distributed, this would be 16x squared, which makes that perfect square in the front here. And then if we do the outers and the inners, that's negative 36x and negative 36x, which we double to get this negative 72x. And then finally, negative 9 times negative 9 is this positive 81. All right, here is number 50, last one for these polynomials. We're going to have to factor the special case polynomial completely. This one looks a little bit intimidating at first, especially because we have some bigger numbers here. But I think I'm going to do first is see if there's a GCF between this term and this term over here. What are they both divisible by? Well, on the side here, let me see. So let's see, we have this 243 and then we have 48. Let's see if they have any common factors here. I think we can divide these both by 3. 2 plus 4 plus 3 is 9, so it's divisible by 9 and 3. 48, 4 plus 8 is 12. 12 is a multiple of 3, so we can divide these both by 3. If we do that, we're actually going to get 81, and we're going to get 16. And I think these are relatively prime, but it's kind of nice here that 81 and 16 are both perfect squares. So let's go ahead and do this. Let's take this 3. That was the common factor, or the GCF. And then if we take that 3 out, we're going to be left with 81x to the 4th power minus 16. Okay, so we just factored out a 3 as our GCF. And this is actually pretty helpful to us because this right here is a perfect square, and this right here is a perfect square. So if we just kind of write that on the side here, it's 81x to the 4th power. If we go ahead and take the square root of that, that is going to equal, the square root of 81 is 9. And then the square root of x to the 4th is just x to the 2nd power. Now, what about this 16? That one's a little bit easier, right? If we take this 16, take the square root, then that's going to be equal to 4. All right, so we know the square roots of both of them, so try to remember that pattern we learned earlier. This is a difference of squares. Again, we have a subtraction sign and we have two perfect squares, so it's a difference of squares. And if you need to look back at the pattern, you can look at 48 over to the left of the screen or back at another one. And so we always get the square roots, which is going to be 9x squared. And we have another 9x squared. And then we have a 4 here. So there's a 4 and then another 4. Difference of squares always has a plus and a minus, so we can add one plus sign and one minus sign. Now, before you think you're completely done, we can actually factor this a little bit more, right? So this is done. This 3 on the outside. This is also done. There's no such thing as a sum of squares that we will factor. And then over here, this one is actually interesting because this is also another difference of squares. So let's just take a look at this 9x squared minus 4. And so this one we can actually do again. So if we take this 9x to the second power, and we go ahead and take the square root of that, you can see it's a perfect square. That's going to be equal to 3x. And then if you take that minus 4, or just the 4 rather, take that 4 and take the square root of it, you're going to see that that's equal to 2. So because it's a difference of perfect squares, we can factor this further again. So in the beginning here, we're just going to have this 3 multiplied by this 9x to the second power plus 4. And then what did we just figure out over here? We figured out that for these two binomials, we're going to have this 3x plus 2 and then 3x minus 2. So this one had a lot of steps here, but if you wanted to say this is completely factored, we'd have 3 multiplied by the quantity of 9x squared plus 4 multiplied by the quantity of this linear binomial of 3x plus 2 multiplied by the linear binomial of 3x minus 2. So this here would be the completely factored form. We just had to do the difference of squares pattern a couple times here, just because we had a higher exponent and it happened to have a perfect square inside of a perfect square. Alrighty, now on to the sixth and final part of this Algebra 1 review. For part 6, let's take a look at quadratic equations and functions. For 51, we have the length of Benny, who's a dog. His play area is going to be 2x plus 5 feet wide, and the width is going to be 3x minus 4 feet wide. Okay, so we're just going to go ahead and assume that this is going to be a rectangle, because most play areas probably would be, and it doesn't say anything otherwise. So if we just have a rectangle here, we can just go ahead and say that one of the dimensions is going to be this 2x plus 5 feet, and the other dimension is going to be 3x minus 4 feet. Doesn't really matter, because if we're finding the area of a rectangle, remember that area is going to be length multiplied by width. And so if we have these two dimensions here, we can say the area is going to be equal to this 3x minus 4 binomial multiplied by this 2x plus 5 binomial. All right, what we can do there is just do a little bit of distributive property and FOIL this out. So if we go ahead and multiply 3x times this 2x right over here, and then this 3x multiplied by 5, we're going to end up with 6x squared and then plus 15x. And then if we go ahead and distribute this -4 and this -4 to both of those terms, we're going to end up with a -8x and a -20. All right, we can then just go ahead and combine these like terms in the middle, this positive 15x and -8x. And so the area here is going to be 6x to the second power and then plus 7x and then minus 20. So if we're writing an expression to represent the area here, then it would just be this 6x squared plus 7x minus 20. This would be that trinomial expression, and the area would be feet squared, just because this is a two-dimensional measurement as opposed to one-dimensional. For 52, we're going to go ahead and rewrite a quadratic function in vertex form and then state the coordinates of the vertex. Now I'm going to make a real rough sketch here. So, okay, we have this quadratic and it's written in standard form. So it's f of x is equal to that ax squared, where a is 1, plus bx, b is 14, and then we have plus c, and c is 33. So to rewrite equations in standard form into vertex form, what we're going to do is we're just going to group these first two terms over here, this x squared plus 14x, and then we're going to write this plus 33 on the outside here. Okay, so it doesn't change anything, we're just grouping it this way. And we have to take a look at this part, this x squared plus 14x, and we have to complete the square there. So we're going to have this x squared plus 14x, and then we're going to have to add some missing value here. And if we're going to add that value, we're also going to have to subtract that value to balance this whole thing out. All right, so you might remember earlier when we completed the square, what we did was we took a look at the b term. This is the 14, and we're going to take that b term of 14, so 14, and we're going to cut it in half, and then we're going to go ahead and square it. Okay, so 14 divided by 2 is 7, and then 7 squared, that's going to equal 49. So the value that would complete the square here is going to be 49. And if we're just randomly adding 49 into this function, we should also subtract 49 so that we're not actually changing the problem, right? So at this point, we now have a perfect square trinomial. So again, if you forget what that is, you can look back at one of the previous problems, but this should factor into the quantity of x plus 7 times the quantity of x plus 7. And then we still have this plus 33 minus 49, but we can combine those constants, and that would be negative 16. So I'm going to write minus 16 here. All right, now let's go ahead and take these two identical binomials and just condense it and just say this is the quantity of x plus 7 squared and then minus 16. This right here would be the function written in vertex form. Now, if you happen to forget what vertex form is, it's f of x is equal to a times the quantity of x minus h squared, and then it's plus k. The vertex of a quadratic written in vertex form is just the coordinates of h comma k. So if we go ahead and write the vertex here is going to be h comma k, then what does that mean in this case? Well, h has to be a negative 7, just because it says plus 7 in our function, so it must have been a minus 7. And then k has to be a negative 16, just because that minus 16 means we're adding a negative 16 to it. So that's the vertex. Because our a value for this function is just going to be this invisible 1 that's in front, we know the parabola is going to open upwards because it's a positive leading coefficient. If it was a negative, then it would open down. So if we were making a rough sketch here, I would do something like this. If this is the x-axis and then this is the y-axis, then we would know that this vertex of negative 7, negative 16 would go to quadrant 3 somewhere, so 7 to the left and then 16 down. We could plot something maybe down here roughly, and then we were going to go ahead and just draw this parabola opening upwards. So very rough sketch here, but it's nothing too specific, just a little drawing to help you kind of understand what this would look like. If you wanted to be more particular, you can make a table and then plot some more points down and make it much more accurate. All right, let's take a look at 53. For 53, we're going to determine the zeros of the function by factoring, and then we're going to sketch this graph. Okay, so here's what I'm going to do first. When it says determine the zeros, that means we're going to set the whole function or equation equal to 0. And then on the right side, I'm actually going to factor out a negative so that we can just deal with positives here. So it's going to be 12x squared, and then we factor out a negative, that'll be plus 11x, and factor out that negative would be minus 15. Okay, so when I factor, I basically look at factors of this leading coefficient of 12x squared. So I'm going to maybe start with 4x and 3x. Those multiply to get 4x squared, right? And then I'm going to take a look at this minus 15 at the end, and I'm going to choose 5 and 3. Those multiply to get 15. It's a negative 15, so let's make one of these signs negative. And then let's see here, if we multiply across, this will be negative 20x, this is positive 9x. Negative 20 plus 9 is negative 11, but since we're looking for a positive 11, let's just go ahead and make this a positive 5 and a negative 3. So that if we multiply here, we would get positive 20x minus 9x, and that does get us that 11x or positive 11x that we're looking for here. All right, so we can say 0 is equal to negative times, and let's see what this is going to look like. We are saying that we know 4x and 3x are going to be our first terms in those binomials. The 4x is being multiplied by the 5, so I'm going to go ahead and put a positive 5 over here, and the 3x is multiplied by a negative 3, so I'm going to put that negative 3 here. So that's the negative 3, and that's the positive 5. All right, so if you see that these two are paired together, those are our outers, and if these are paired together, those are our inners. Okay, and so this would be the factored form here. Now, if we're trying to find out what the zeros are, we just take this binomial and set it equal to 0. So if we do that, we can solve for when the graph is going to hit the x-axis. So going ahead and solving this, we can see here that x is going to equal 3/4. Okay, so one of the zeros we just found out here is going to be when x is 3/4, this function will equal 0. All right, now we're going to do the same thing over here and set this equal to 0, because if this binomial is equal to 0, then the whole function will equal 0. So go ahead and set it equal to 0, and then solve for x. If we go ahead and do that, we find out here that 3x will equal -5, which means that x must equal -5/3. So what's the 0? It'll be -5/3, comma 0. Okay, so those are going to be the two zeros of this function, or the x-intercepts. Now making just a very rough sketch here, if this is our x-axis and then this is our y-axis, all this really means here is that this positive 3/4 would be maybe somewhere over here. -5/3 is more negative. It's maybe somewhere over here to the left. And then the other thing we want to notice here is that our leading coefficient is -12, or we have a negative in front here, which means our parabola is going to open downwards. So I'm not going to find the vertex and make it more accurate, but just rough sketch here. This is what our function is going to look like. We know it's going to open downwards just because we know that the a value is negative. All right, here is number 54. We have an equation here, and so let's see what's going on. I think we're just going to start by rewriting the equation. So we have x times this 18 minus x, and this is going to be equal to 2 times the quantity of 9x minus 32. All right, so to start, I'm just going to distribute this x to both of these terms here. And if we do that, we're going to get 18x minus x squared. And then on the right side of the equation, we can go ahead and distribute this 2 as well to both of these terms. If we do that, we're going to get 18x minus 64. Okay, so let's go ahead and solve this equation. Let's maybe put everything into the same side to make it in standard form. But I do notice that there's 18x on both sides, so this might be nice if we go ahead and take away 18x and take away 18x. If we do that, then we don't have to deal with those at all, which is kind of nice. On the left side, we'll have negative x squared, and on the right side, we'll just have this minus 64. Let's go ahead and add x squared to both sides, and add x squared over here as well. And if we go ahead and do that, we're going to see that this is going to be 0 is equal to x squared minus 64. Now at this point, you should hopefully notice, or if you didn't, we see this pattern of difference of squares. And so we should be able to factor this right side into the quantity of x plus 8 times the quantity of x minus 8. Okay, you could have solved this equation by square roots too if you wanted to. I'm just choosing to use this pattern to help you get a little better at it as well. But if you set this equal to 0, x would equal -8. And if you set this equal to 0, x would equal +8. So what are the solutions here? We can say that x could equal a positive or a -8, or we can write plus or minus 8. These are the two solutions that would make this equation true. All right, here is 55. For 55, it says determine the axis of symmetry of the graph of this function. All right, so you can do this a couple different ways. You could use that So you can go about this in a couple different ways. If you wanted to go for the AOS right away, you can just use this formula of x is equal to the opposite of b over 2a. And you can see here that b is equal to +16 and a is equal to -4. So that's one way we could do that. We can say that x would be equal to -16 all over 2a. So that's going to be 2 times -4 or -8. You can see here that x equals 2 would be the equation of the vertical line. That is the axis of symmetry. So that's it pretty quickly, but sometimes it's hard to kind of visualize what's actually going on. So I'm actually going to go about it a different way to hopefully help you understand what's going on here as well. Let's set this equal to 0 and find the intercepts first, because I think this is going to work out nicely. We factor out a negative again just to make some more positive coefficients. This is going to be 4x squared, then -16x, and then +15. And let's see if this factors nicely. For the 4x, I'm thinking we could try something like 2x and 2x. And then for the 15, I think we're going to do like a -5 and a -3, since we have a -16 in the middle, but a +15 at the end. And so if we go across, this is -10 and -6. Oh, that works out nice. That is negative 16. So these are going to be my pairs here for my binomials. So let's go ahead and open up these parentheses. And it looks like we're going to have this 2x, and then I guess technically they're just both 2x's here, right? And then minus 5 and minus 3. Okay, so if you set each of these equal to 0, then you're going to find out that x is going to equal 3 over 2. And if you set this one x equal to 0, or this binomial equal to 0, you're going to get x is equal to 5 over 2. Right? So if you look at this on a graph, I think this is kind of helpful to see. So if you ever already have it in factored form, or you know the zeros, you can go about it this way as well. So visually speaking here, this 3 over 2 is over here. It's 1.5. 5 over 2 is 2.5. We know we have a negative leading coefficient of -4. So for our graph, it's going to open downwards. It's going to look something like this. Okay, and what about the AOS? Well, the AOS has to be this vertical line that is right in the middle of the two intercepts. Now, what's in the middle of this 3 over 2 and 5 over 2? Well, the average of 1.5 and 2.5, again, this is 1.5 essentially, right? And this is 2.5. What's right in the middle of those two? That's just going to be 2. So when we have this AOS and say that that's x equals 2, you can also just find the average or the middle of the two zeros, or x-intercepts. So that's going to be the equation of the axis of symmetry. It's just that x equals 2 equation of a vertical line of the graph of this function. But there's two ways in case it helps you visualize and understand a little better. For 56, we're going to go ahead and solve this equation by factoring. This leading coefficient is 2, so I'm going to put maybe a 2x and a 1x. 2 is prime, so it has to be 2x and 1x. So just for starters, hopefully that helps you out, because we know, oh, I forgot to put the 0. Let's put it over here instead, that this is going to start off with 2x and 1x. So it kind of helps take off some guessing work. And also we have a prime number over here of -5, so that makes our life really easy actually. So we know the factors have to be 5 and 1, right? No other choice. It's a -5, so I'm going to put the negative here on the 1. Hopefully you'll see why here. If you go diagonal, x times 5, that's 5x, and 2x times -1, that's -2x, and then 5x minus the 2x does get you the 3x. All right, now this 2x is paired with the -1, so that means this 2x is going to pair with the, and then put the -1 right over here. And then you can also see here that this x and 5 are being paired, so this is the x, and there's only one more spot to put the 5, so we're going to put a +5 right over here. Okay, now that we have linear binomials, it's pretty straightforward to solve for the solutions here. And so we just set this equal to 0. So we say 2x plus 5 equals 0. If you subtract 5 from both sides, 2x equals -5. And you divide both sides by 2, x equals this -2.5 or -2.5. And if you set this one equal to 0, we can say x minus 1 equals 0. If we add 1 to both sides, x equals 1. So what are the two solutions here? We can say x equals -2.5 or 2.5, or we can also say, we could say that x is equal to 1. All right, so those will be our two solutions. All right, this is 57. For 57, we have a system of equations. This top one here is going to be linear, all right? It's going to be a straight line. We know that because the highest power is 1, it's 3x to the first power. And then the second one over here, this one is quadratic, all right? So if we are trying to visualize what this is looking like, we're trying to find out if this straight line is going to cross with this parabola here. So it's possible that a few things could happen. We could have a parabola that looks like this. I'm drawing it opening upwards because I see a is equal to 1. And it could happen where the linear one crosses the parabola twice, so there would be two solutions here and here. It's also possible that if we were to solve this, that the linear line would actually just touch it, its tangent to it, that's a fancy word, and it would just have one solution. That's possible, right? And a third possibility is if you have a parabola and the linear line just is below it or above it depending, and there's no solution. So three things could possibly happen here, and we're going to see if there's either no solution, one solution, or two solutions. Now, if you see that this is y equals 3x and y is equal to x squared plus 3x minus 16, then we can use substitution, right? If y is equal to both of these things, then this 3x should be equal to this x squared plus 3x minus 16, right? Hopefully that makes sense if they're both equal to each other. So we should be able to say that this linear part of 3x is going to be equal to that quadratic part of x squared plus 3x minus 16. Okay, so this is a quadratic equation that we can hopefully solve. I'm going to start by taking away 3x from both sides. And hopefully you're going to see that these 3x's are going to cancel out nicely. So we're going to get 0 is equal to x squared, and then it's just minus 16. Surprise, surprise, we have another nice pattern here. This is the difference of squares. It's a perfect square minus a perfect square. So 0 would be equal to the quantity of x plus 4 times the quantity of x minus 4. Okay, so what are the two solutions here? If we set this one equal to 0, this x plus 4, we're going to find that x equals negative 4. And if we set this one equal to 0, then x would equal positive 4. Okay, now what are the actual solutions? Well, first we're going to take this negative 4 and we're going to substitute it back into either one of these equations. You could either do it here or you can do it in the quadratic equation, but plug it into both spots. Hopefully you can see that the linear one's going to be a lot easier. So when x is negative 4 times 3, that would be negative 12. So we know y would be equal to negative 12. That being said, if we do the same thing with this 4, and we plug it in, again, I'm going to choose the top one because that's easier. 3 times 4 is 12, so y would equal 12. So what does this all mean? This just means that the two solutions here, one of them is going to be at negative 4 comma negative 12, and the other solution is going to be at positive 4 comma positive 12. All right, so these would be the two solutions, or the 2 points at which these two lines are going to intersect each other. So you can maybe think of this negative 4, negative 12 as the point over here. It would be down in quadrant 3 somewhere, and this would be the point in quadrant 1 at which they intersect each other. Here is 58. For 58, it says if f of x is equal to 3x squared plus 4 and g of x is equal to 2x minus 3, what's f of x plus g of x? And also state the domain and range. Okay, so we're going to add these two functions together. If we have f of x plus g of x, we just have to add what their functions are to each other. So the f of x function is just this 3x squared plus 4. And we're adding that to g of x, which is going to be this quantity of 2x minus 3. So if we're adding two polynomials together, we can just combine like terms because the plus sign and the parentheses don't really matter too much. We don't have to just distribute in positive 1. So we have 3x squared. The 2x has no like terms either. And then the 4 plus negative 3 is just positive 1. So that's going to be what f of x plus g of x is. That's what this function is. And then what about the domain and range? Well, I think what we're going to do is maybe sketch this first or figure out where the vertex is so we get a better idea of what's happening. It's definitely opening upwards because this is going to be a positive a value, but we don't know where the vertex is yet. So let's go ahead and figure that out. I'm going to start by finding that AOS, or the axis of symmetry, because that tells us the x value of the vertex. So again, that's x equals negative b over 2a. And then so negative b would be negative 2, and 2a would be 2 times 3, which would be 6. And then so this simplifies down to being negative 1/3. Okay, so that's going to be the AOS, or the x value of the vertex. Now let's go ahead and take this x equals negative 1/3 and plug it into this function here. And that way we can find the y value for where the vertex is. All right, so let's go ahead and take this negative 1/3 and say that's going to be 3 multiplied by this negative 1/3. Go ahead and square that, plus 2 multiplied by this negative 1/3, and then plus 1. Okay, so negative 1/3 squared is going to be positive 1/9, so we have 3 multiplied by 1/9, and then 2 times negative 1/3 is just negative 2/3, and then we're adding 1, which is just, I'm just going to write 3 over 3 just so we have all fractions here. 3 times 1/9 is going to be 3/9, which is simplifies down to 1/3. So 1/3 minus 2/3 plus 3/3. Now 1/3 minus 2/3 is negative 1/3, plus the 3/3 is going to be positive 2/3. So that's going to be what the y value is equal to. So the vertex we just found out here is going to be at negative 1/3. That was that AOS value, comma 2/3. And that's that y value that we just found out. All right, so if you're wondering what this graph generally looks like, I'm just gonna make a really rough sketch here. Again, we know it's opening upwards because A's value is equal to 1, but we also know where the vertex is. It's at -1/3, comma, 2/3, so that would be maybe somewhere here in quadrant 2. And we know the graph is gonna be opening upwards again, like we said, so the graph would look something like this. Again, we know where our vertex is, and that AOS was just that dotted line, vertical one that says x equals -1/3. Right? That's the AOS here. All right, so what's the domain? Well, the domain for all quadratic functions that we have here are gonna be all real numbers. So x can be all real. That's that symbol for all real. If you wanna use interval notation, we're gonna say the function technically goes to the left forever and it goes to the right forever. Now for the range of this function, this is just the lowest y value to the highest y value. And so y just has to be greater than or equal to the lowest y value. So what's the lowest y value here? The lowest y value is this 2/3 we just found out. And so y has to be greater than or equal to 2/3. Or we can say in interval notation, 2/3 is the lowest it can be, put a bracket on it. But the graph does go up forever. So we say it goes up to positive infinity. All right, here is 59. For this one, we have the function h of t is equal to -16t squared plus 40t, and this models the height in feet of a ball t seconds after it's thrown in the air. What is the maximum height of the ball reaches after it is thrown? Okay, so we have this function h of t, and it's equal to this -16t squared plus 40t. And when we're doing these, I think what a good idea is if we find out where it hits the ground, that might make it easier for us to figure out where the AOS or the top of this ball is going to be. So if we go ahead and set this equal to 0, we can say 0 is equal to, let's factor out the GCF here of -8, and we can factor out a t as well. And then we're gonna be left with 2t minus 5. So why is this helpful? Well, factoring this, we can see that if this whole thing's supposed to equal 0, then what would make this equal 0? Well, if -8t were to become 0, if you divide by -8 and divide by -8, then t would equal 0. So at time 0, the ball's on the ground. And over here, if we set this equal to 0 and say 2t minus 5 is equal to 0, if we add 5 and add 5, we see here that 2t is equal to 5. And if we divide both sides by 2, we can see that t is equal to 2.5. So what does that mean? It means that at 0 seconds, when time is at 0, the ball's on the ground because it's set equal to 0. And when time is 2.5, the ball hits the ground again. So I think this is important because if you are wondering what is this happening visually here, then we're saying that if you look at a graph, at time 0, you have this intercept at 0, 0, and at time 2.5, that's over here, the ball is on the ground, it goes up, and then eventually it comes back down at 2.5 seconds. So the question is what's the maximum height? Well, we've been practicing figuring out our AOS for a while, and that helps us find when that maximum height is going to happen. So if t equals 0 is right here, and t equals 2.5 is over here, then what's the middle of those two? Well, the middle of 0 and 2.5 is going to be 1.25. So we can see here visually that the AOS is x equals 1.25. So this x equals 1.25 is really just saying t is equal to 1.25, but as a fraction, I'm just gonna leave this as 5/4, just because that's gonna be easier to plug this in. So at 5/4 seconds, we are at the maximum height. So let's go ahead and just take this 5/4 and substitute it in here to figure out the actual height here, okay? So plugging it in, we are going to have, let's see here, we're gonna have -16 multiplied by this 5/4 squared, and then plus 40 times this 5/4. If we go ahead and square this, we're gonna have -16 times, what is this, 25 over 16? And then if we go ahead and multiply the 40 times 5/4, the 4 and 40 are gonna cross cancel, so we're just gonna end up with 50. And then if we multiply -16 times this 25 over 16, the 16s will cross cancel. We'll have -25 plus 50, and that's equal to +25. So what we just found out here is this maximum height is going to be 25. So what's the maximum height? We're going to say it's going to be 25 feet. There we go. All right, one final problem for number 60. Let's go ahead and determine the zeros for the x-intercepts for this function. So just like earlier, when we're finding zeros, we're really finding out when the y value is 0 or where the graph crosses the x-axis. So starting off, we're going to set the f of x equal to 0, and then we have this x squared plus 2x minus 8. So this is a quadratic here, and then we have a linear binomial of x minus 6. Okay, so when do we find out these things are equal to 0? Well, to start, we already know when the function is equal to 0 looking at this one, because if we set this equal to 0 and say x minus 6 is equal to 0, and if you add 6 to both sides, then x would equal 6. So we know one of the zeros here from looking at just this linear binomial is going to be at 6, 0. Right? If x was equal to 6, this whole function would equal 0. Now, what about this trinomial over here? Well, this one's factorable, and so you just have to set this equal to 0 and say x squared plus 2x minus 8 is equal to 0, and then you got to factor it. So I think it's going to turn into x plus 4 multiplied by this x minus 2, and that would equal 0. Now, when would this whole thing equal 0? Well, you got to set each part equal to 0. So if you set this equal to 0, then x would equal negative 4. If you set this equal to 0, x would equal positive 2. All right. So if we're looking at just this part here from the trinomial, we have two zeros that occurred. One of them was going to be, we just wrote that down at the bottom. If x is negative 4, the function would equal 0. And if x was 2, then the function would equal 0. So what are the three zeros here? We have negative 4, 0. That's one of the x-intercepts. Then we have 2, 0. That's another x-intercept. And then we have 6, 0. That's the third x-intercept. So this is what we call a cubic polynomial, okay? Just because we have something raised to the power of 2, multiplying something with the greatest degree of 1. So using those exponent rules, we get something with degree of 3. If you're wondering what this is gonna look like, it's gonna look something like this, where if we graph it, we have a leading coefficient that's positive, yeah? And then if we go ahead and see here, negative 4 would be maybe somewhere over here, positive 2 would be somewhere over here, this positive 6 would be somewhere over here, and our entire graph would look something like this, where the graph is increasing, crossing there, and it's gonna reach a higher point, and then go back down through, and then it's gonna come back up. So really rough sketch here, but this is called a cubic function, and that's what happens when you multiply a quadratic function by a linear function. So that's what it would visually look like when you look at those x-intercepts. Alrighty, so there you have 60 different practice problems dealing with Algebra 1. Hopefully you found it to be a helpful review on some of these topics that you may wanted to just brush up on, or maybe just learn just because you're interested in strengthening your background on this. If you found the video helpful, please consider giving it a thumbs up and sharing with a classmate or friend who might also find it helpful. And as always, keep up the great work that you're already doing, and I'll see you in the next one.